Yo, what's up, everybody? Welcome back. Today, I want to do a Hello World to 3D animation setup in one sitting. So the context here is we've been kind of working over the past few weeks on like designing a character for some game and getting his animation imported into like an OpenGL like game engine that we're working on, right? And at the end of last happy hour, we kind of got to this point where we have our guy in here and he's looking pretty good. We've got his like running animation, he's got a little bit of shadow on him, he's got his like eyeballs textured and his like little wooden sword and shield, right? And I was just like kind of taken aback by like the idea here that nothing from like literally like putting pixels on the frame buffer to here, nothing is that complex. And I just think that there's something really cool and like beautiful about the idea that like you take a bunch of like small, not that complex ideas and you put them together and you get something that's like, you know, relatively complex. Obviously, this is so far from like real 3D like AAA games are like a whole different level of complexity and stuff like. But getting something that looks like this is like it's not that hard, but it at the same time it is like a lot of stuff, right? And I think that's cool. And so I wanted to kind of like collect all of the principles required to get to this point from nothing in like one spot, because I think it's kind of cool to like show the progression from like I know nothing to like I'm doing this now. And I think that's like I think it's cool. So what I wanted to do is I just wanted to like basically implement this again, but because like this information is scattered over 2 weeks, just do it all at once. And we can kind of imagine this as like we've been studying for the final exam and today it's time to write it, right? We'd have all this stuff, but it's like it's just nice to kind of prove to ourselves that we understand all of the concepts well enough to do it again. We didn't gloss over anything. We didn't like cheat and copy paste something to the point where we didn't understand it. So yeah, that's the plan. I think we're just going to work in C today because I just think that like copy pasting some stuff for like initialization will just be a little bit easier in that land than working in Zig like we do usually. I think if we worked in Zig, we'd be wasting like a fair amount of upfront time trying to like get our initial OpenGL example working. But yeah, that's the plan. That's the plan. So we have little environment that we set up. We have GLFW for window initialization. Again, this is like something that we could theoretically do ourselves, but it's just like too much to do right now. LibGL, because if we're gonna like put stuff on the screen, you kind of need like to go through the GPU, right? Like my monitor is like physically plugged in to like my tower, and in the tower there's like a GPU right here and he's plugged into here, right? So somebody needs to kind of like put the pixels into this guy, right? And so OpenGL is like our mechanism of doing that. I'm thinking of it as like standard library of like drawing stuff, right? There are other like mechanisms to do this, but OpenGL is like fine. It's like, you know, good balance of like simple and powerful enough to do what we want to do today. Clang tools just and to do so I get like autocomplete in CLand, Python because we're going to be doing some like pre-processing of data and it's just easier over there, and then Python language server so I can get autocomplete. So that's what we're set up with. And I think step one is to just get a like window with something drawn in it. So this is one of those things where it's like I'm not above searching GLFW hello world, right? I know how to like write this stuff. There's a lot of like kind of like finicky things that you can get kind of wrong in your like initial OpenGL setup. So it's kind of nice to just have like a starting point. You know, just so that you have like something that you know works. Why can't I paste? Hello? Copy? Paste? There we go. Okay, so their example, though, does have some stuff that we don't have. They have some sort of like linear algebra library that we don't have. They're also using like an OpenGL loader, and at the very least on Linux with Mesa, you can get away without that. If you kind of just do like define glx prototypes or something, this should get us everything we need. Like normally when you start up with OpenGL, there's like this idea that there are like many OpenGL versions and they all have like different capabilities. And so there are these things called like OpenGL loaders, and they basically like dynamically figure out which things are available and expose them to you in a way that like doesn't suck. But we know that like we have latest OpenGL and like we will always have latest OpenGL. So we can just kind of hard code like, don't worry about it. Use the fucking latest and greatest. We don't have their linear algebra library, which means we're missing their vec2 type and vec3 type. But I think we can probably just get away with like, probably we can just make this 2 floats, and this 3 call here is probably color, so we can probably get away with that. And then skimming down here, they have like OpenGL loader stuff that we're not doing, and then we're just gonna like not do their matrix multiplication stuff, which means that we're just gonna take out the matrix multiplication from here as well. Okay, so I think that this is an initial state that works. Let's just see, and then we'll kind of talk about like what is in this thing in a second once we know that it works. Okay, cool. So we have a little triangle rendered to the screen. So what did we copy paste here? Because we don't want to just copy paste blindly, but we did want to like start somewhere. So what are they doing? OpenGL. OpenGL kind of works in this world where you have like a GPU running some code, right? You have like GPU, GPU, and he's gonna do like lots of like floating point multiplications, float multiplications, and like maybe some adds as well. And then he's also going to be doing some sort of like draw to screen, right? That's kind of like his job, right? And so what this program is doing is we're kind of defining like what these actions are going to be. So like OpenGL land, you have this thing called like a vertex shader, which basically says like, for each point on this triangle, let me do some math to it, right? Which would let you do things like, if you want to like move the triangle around the screen, this becomes really easy because you can just like in your vertex shader say like move all of these to the right, and then your triangle will move to the right. This then, once you have like kind of like the corners of your triangle, this goes into like a fragment shader, they call it, where fragment shader, you can kind of think of it as like, I'm going to do something for every pixel on the screen. Hand wavy, I guess every pixel on a polygon that's like visible to the screen. And so in the fragment shader, they're going to like take this triangle and they're going to like chunk it up into pixels, boom, 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 you know, kind of pretend that these are reasonable pixels, and you're going to like do an action for each of these pixels, right? And so their vertex shader basically just says set the position to whatever we input from some like buffer of data. And then their fragment shader says color that thing according to the color that they pass through to us. So we say like our data buff, we like provide some data for these programs to act on. This program has positions and colors. So like the first vertex of the triangle is at this position with color red. The second one is like, this is like bottom left. This is bottom right with color green. And this is top with color blue. Right? So if we look at the output of this program, oops, can we do like a little main? Right? So we see like red over here, green, blue in the middle. And then like for each pixel here, because like our vertex shader only runs for each of these 3 points, but the fragment shader runs for like all of the pixels in the polygon, they kind of like interpolate anything that's forwarded from the vertex of the fragment shader by doing this thing called like barycentric interpolation, which is basically like any data that you get passed in, if you're like in this triangle, right, and you're like here, you're at this point, you can kind of like draw this shape, right? And hand wavy, it's like if you call this A, B, and C, and then we'll call this like little a, little b, and little c. Any parameters associated with A are like used proportionally with like the area of big A over the area of the whole triangle, right? So if you're like kind of really on like this edge right here, the area of like big A is 0, which means that the stuff from little a is not used at all, and we're interpolating just between these two values. And they just kind of like linearly interpolate between those. Hand wavy. There's like some stuff like perspective correction and stuff, but we're not going to worry about that right now. And then like otherwise, all this code is doing is he's like initializing like an OpenGL context. I'm just going to say that I want OpenGL 4.6 here. I'm going to make this thing square because it's like kind of like just easier to reason about if our window is square. He's doing some like key callback stuff for like input processing. We don't need to do that, so I'm just going to delete that. And then here he's basically saying like, I have some data and I want to put that data on the GPU, right? So if we are going to like render this triangle, we need to give him like the 3 points on him, right? 1, 2, 3 with like the colors and positions. These things are like in memory on the CPU here, right? And we have like basically like 2 byte or 8 bytes of position data followed by 12 bytes of color data, right? And that happens like once for each vertex. So this stuff is kind of saying like, let me create a buffer that like a buffer on the GPU, right? That's kind of like what this is saying. Then he's saying like, now please, can I like put some data on that thing? And that data is going to come from these vertices, right? So at this point you have like a buffer of stuff, right? You don't really know, the GPU doesn't know how to interpret that data yet, but he has like the bits and bytes, you know, that he can like look at if he wants. Then somewhere else, we then attach that data somewhere. Like we kind of say like, hey, when you run this program, could you please interpret this data such that like the first 2 bytes are position data and like the next 3 byte, or sorry, the first 2 floats are position data and the next like 3 floats are color data. Hand wavy. So if you want to move a triangle with WASD keys, for example, you need to implement this logic in the vertex shader. Kind of, yeah. So you would do it that way, right? Because like if you were to render like a 3D model that has like thousands and thousands of vertices, like it's easier to get the GPU to like move each of the vertices on that thing at once versus like you doing it on the CPU by hand. Yeah, so like what Erker said, he basically said, so yes, kind of as well. This is all basically like compiling this code for your GPU. So like we're kind of saying like, hey, our GPU, like we have like this text representation of this thing, but like our GPU doesn't execute text. So we need to like compile this for our specific GPU. So that's kind of like what this stuff is doing. Here I kind of want to not do what they were doing here. I kind of just want like hard code 0 and 1 here. So here when we're telling the program, hey, this is how you need to interpret data, we're basically like binding data to the inputs of the program. And so here you can just kind of say like layout location equals 0 to say like the thing at number 0 is the color and the thing at 1 is the position. And then down here we just kind of bind it and say 1 is position, 0 is color, I think is what we just said, right? Then in our like main loop, they basically just like set the window size to match like the frame. Where we're drawing needs to match the window size. They clear everything so that like things from last frame don't kind of sit around there. GLU's program, GL1 vertices. This is saying like use the program that we compiled with this data that we defined, then draw some stuff. Essentially, is it? And that's kind of like the whole thing. So unlocked concepts there are vertex fragment shaders. Kind of like binding data to GPU. Barycentric like interpolation, right? But like none of these concepts are that crazy, but this is kind of like what you need in order to like get something drawn on the screen. Okay, so we have a triangle. Don't know what a uniform is, but I get the idea. Yeah, we'll cover uniforms in a bit. In fact, I think that's the next thing we want to do. So say we want to like rotate this triangle, like let's have it like spin or something, right? Well, how do we do that? Well, we have like, if you were to like graph the data of this triangle, you would kind of have like 1 point over here, 1 point over here, and 1 point here, right? So this is kind of like 0, 0. And we kind of want to do some sort of rotation where like we take this guy and all of the points rotate by some angle, right? So this point is the easiest to think about first because it's like directly on the y-axis. So if we want to take this point and rotate it down to here, this is like, you can imagine this as like, can I draw this bigger so that it's like, so I want to take this point and rotate it like down to like here. So you can have like, you know, your start thing and then your like end state. I just want like colors that you can see it. And you're gonna have like some angle here that you're rotating by. So if this, let's just say theoretically, this point was at like 0, 1, right? He's at 1y, 0x. The location here can be pretty easily determined because like you know that the length of this orange line is like 1 and you know this angle, right? Which means that you have like a right angle triangle where you're trying to find the like x and y values, or sorry, the x and y values, which just means that like using some like high school trig, you have x is going to be sine theta, but it's going to be negative because it's in the top left, and the x or the y value is cos theta, right? Because this is like your high school trig shit, right? So Katoa. And if you want to let's just say for a second that you wanted to do something that was at the same point on like 1, 0, so it's like you're doing the same rotation here. You're bringing it up to this point. You've got like this angle theta again. Now you have y is your opposite side and x is your adjacent. Both sides are positive. So in this world, you have like x is cos theta and y is negative sine theta. And what's kind of sick is that every other point can kind of be broken down into these two concepts, right? So if you have like a point that's not axis aligned, this point here, this is actually like first a movement along x by this much, then a movement along y by like this much, right? And if you rotate this thing, this just becomes kind of like a rotation in like new x by some amount and then a rotation in new y by some amount. But you're kind of like rotating these two vectors independently. Positive sign, no? Did I write negative sign? I did write negative sign. You are right, that is positive side. Right, so you can kind of like break this down into like its two components, which means that if we can, yeah, you just do these for the individual components, right? And we're gonna unlock the next concept, which is linear algebra. So there's like a nice way of representing this where you can kind of just like put numbers in a box. You put these 4 numbers in a box. This guy gets cosine, this guy cosine, sine, negative sine, cosine, right? And so this kind of matches like the x component goes like here and the y component goes like here, right? And the way like matrix multiplication works hand-weightly is like here you're going to multiply by these two numbers, like your x and y position, like this. You're going to put x, y, and the rules for this thing are that you multiply kind of like this by this and y by this, so you get like cx plus sy, and this is like your new x value. And then you do the same thing for each row. So then you multiply the x by this and the y by this, and so you get like negative sx plus cy, right? And so if you plug in like x is 1, y is 0, you get this is backwards probably. Yeah, this should be positive and this should be positive and this should be negative. Yes, because this is positive, this is negative. Because now if you plug in 1, 0, you get cosine sine, and if you plug in 0, 1, you get negative sine cosine, which is exactly what we wanted. So like GPUs or like OpenGL, I guess is probably the way to say this, is like OpenGL gives us like the utilities to represent numbers this way very easily, right? If we go into our like vertex shader that is manipulating, you know, per vertex, you can say for every single vertex in like the entire world here, like for each vertex that we're processing, I would like to do like give me some sort of like 2x2 matrix that we are going to call rotation, right? And then all we have to do is we take our input position and we multiply that by the rotation. And this like multiplication is going to do like, you know, this shit. This like multiply these, add these, essentially, right? So all we have to do now is like define this thing. So I think let's just make sure if we define this as like mat to vec to 1, 0, 0, 1. So if we define this matrix as like 1, 0, 0, 1, that's like no rotation because the X component will be used on the X line and the Y component will be used on the Y line. So it's like XY just maps to XY. And so this is just me making sure that like I got the syntax right here. So if we compile this and run it, we still get the triangle, which is hype. And if we were to do something like, say, invert these, we should get some sort of like inversion of the triangle, right? The blue, we're seeing it like kind of flip over X equals Y. So now the trick is we want to like basically update this rotation matrix from the CPU. So we need some sort of like CPU representation of this thing, but let's just say we have like some like mat 2x2, and he's got, you know, probably like data that's 4 floats, right? Because that it's 4 numbers, 1, 2, 3, 4, and we're gonna represent them as like linearly in memory. If you had like A, B, C, D like this, we're gonna represent that as A, B, C, D like this, right? I don't like tabs here. I can do shift width equals 4, tab sockets 4, expand tab. There we go, perfect. And let's do something that's like, let's get a mat 2x2 according to some like 2D rotation. You know, so like mat 2x2 rotation. And this is going to take in some like angle. We're going to compute like cosine x or cosine angle as cos angle like this. And we're going to compute the sine as sine angle. We need to import math to do that. Bang, bang, boom. And then here we just return a mat 2x2 with these guys. So what do we say? It's like C, what do we say? C negative S, S, C. There we go. So now we should be able to like make that thing. So we're gonna be like mat 2x2 transform is equal to our rotation. I guess we should call this rotation because we haven't unlocked the next concept yet. But let's say that like we rotate by some amount. Now we need to like tell the GPU about this thing. So we're going row major for this. The choice is fine, just pointing out maybe. Yeah. Because I can't think in column major. I'm too stupid to, I know that like it's like better in some ways. There are like benefits doing storing it the other way, but I struggle to think about it that way. So I do row major. I don't think the choice to do row major harms us at all. Unlike our choice to do right hand versus left hand coordinate system. That harmed us a lot the other day. But here, now we can say, hey, GPU, OpenGL land, I would like to upload this thing as like a matrix. So we need to say like we have, I don't remember which one it is. GL uniform. I guess they had a matrix upload in here. Uniform matrix probably 2. So here we're like, we have a matrix that is 2x2 floating point values. And we're like, we are putting this at location 0 because we kind of hard coded location 0 in the vertex shader here. We said this rotation matrix is at location 0, so we can just kind of hard code that there. What else does this guy want? He wants a count. So how many matrices are we uploading? It's just 1. Whether or not we should basically flip this thing over the. So we said we were storing our data like this, right? But OpenGL wants to store it like this. So they kind of want to go like column first, and we want to go row first, just because like I think in rows better. So here we have to say, please, sir, when you go into OpenGL land, could you like flip this shit? Which probably means we need like std bool. And then what was the last thing? The value. So we just like pass in our rotation. Probably like rote data here. And then probably we should do this after we say which program we're using. I assume that, I don't know if it matters, but at the very least, we should do it that like it makes our lives easier. It like makes more sense to me that way. We just link the math library, and now we have like this guy rotated, right? So if we change this value from like 1, so we say like, let's start at like 0 rotation, compile and run, and the triangle should be like upright, right? Then we start saying like rotate by, you know, pi over 2. This should be like a 90-degree rotation, which it is, right, counterclockwise as we expect. And so maybe let's try to like animate this thing. So maybe we can start with like now. How do you do like time in this language? C monotonic clock. It's like clock get time. Yeah. Yeah, that looks right. Why raw? Man clock get time. I feel like non-settable system-wide clock that represents monotonic time. What's raw? Similar but provides access to raw hardware base that is not subject to frequency adjustments. Yeah, I guess it doesn't really matter. Okay, so let's say that we have like some time spec now, and this is clock get time with clock monotonic, and it's actually kind of more like this. Man clock get time. What am I missing? It's time.h. Boom. GLTF has a time function, right? Oh. Well, I know this one, so I'm gonna do this one. But maybe. Let's say that we're going to like figure out the time since the last frame. So we'll kind of initialize this thing like this, and then we'll kind of do some sort of diff here. So I guess we have to write, I think that we have to write a function for this. So if we're like, give me a diff time from 2 time specs. So we have to make sure we get this in the right order. So last probably, and now, I guess we'll call it. GFW get time in seconds since initialization. That does seem kind of nice. But we're already here. So we'll do now TV sec, the time in seconds minus like the difference of the time in seconds. Yes. This is going to be like right here. And then we also have to add in the time in nanoseconds. So it's just like the time in nanoseconds like this, but we need to divide this by some amount. So this is like over 10 to the power of 9, right, for nano to seconds. Yeah. So now if we go here and we go like diff time last now, we probably want to set last to now at the end of loop. And here, this is our like delta S. So we should be able to like update the rotation by some amount. So here, let's say that we have like some like angle. He starts at 0. We kind of make the rotation matrix now according to this guy on every frame. And we are going to increase the angle by like some amount times delta seconds, right? So we're going to maybe do like 1 full rotation per second. So 2 times pi times this. That sounds kind of right. And then we probably want to like make sure that like this guy stays between this and 2 pi. All right. Let's fucking go. So we got our little rotation. Simple. So unlock concepts is like matrix, like vertex, matrix, vec, mat, multiplication. We've unlocked like rotation matrices, and we've unlocked like time, like animation, like, yeah, sure, time. That's good enough. Okay, so say we want to do something more advanced than this, right? Say we don't only want to do a rotation, but we want to do a translation as well. You could do that by saying like in your vertex shader, let's add another thing, right? Let's say that we like at location 1, we take in like a vec2 that is like his translation, right? And you could like offset this thing by like some amount. You could do it that way, except it's kind of convenient if you can express both the rotation and translation in like one concept, right? So you can take like, it would be nice if we could extend this like box of numbers to be a translation as well. And so you can do that kind of. So the way that these like matrix multiplications work, right? You have like everything is multiplied by x or y. And so your translations are kind of independent of x and y. So it would be nice if you could be like, well, what if we just like hucked like a 1 on the bottom of this thing? So we like pass in a 3-dimensional vector and we just kind of hard code the last parameter to 1. That allows you to add like a third column in this guy that has the translation parameters, because no matter what x and y are, you are going to like increase x by 1 times whatever's in this column for x and y. Say you don't want obvious screen tearing. It's bad when I can notice it. It's even worse when I notice via Twitch. I don't see it. It's probably something to do with the fact that like my screen is refreshing at 144 hertz and Twitch or like the OBS is capturing at 60 hertz. Oh, maybe I do see it. Yeah, that's interesting. I can't tell. Yeah, I guess there's probably some. I thought that we were like doing swap buffers. We should like set swap interval. Maybe we're not doing that. GLFW swap interval. So this is supposed to be every frame. So not really sure. Not sure. But we're not going to think about it because we don't have time to do that right now. Okay, so yeah, let's like start upgrading our like 2x2 matrices to 3x3 matrices, right? And so like the idea here is that you kind of have like your rotation parameters in like the top left, like the old 2x2 matrix that we had. Then like kind of like down here, you just write like 0, 0, 1 because like kind of the way that these like matrices compose, it kind of just works out that way. And then this is going to be like your translation in x and y here. Then when you multiply, you have to add in a 1 at the end of your multiplication, but that's fine. There are, we'll kind of like, we'll find reasons why this is like pleasant later. Really, like the big thing is that you can kind of like compose these with like matrix multiplication rules. You can kind of say, give me a box of 9 numbers that represents a translation, give me another box of 9 numbers that represents a rotation, and you can kind of like fold those down into one new box of 9 numbers that does both at once. And you can kind of just do like sequences of operations that will like kind of fold down into one calculation that has to be done on the GPU. But you can think of it as like 10 things done in sequence, which is kind of like nice. These guys like compose in a way that's like very nice that way. So let's upgrade these guys to 3x3 matrices. Our rotation now is going to kind of look like this. We throw some zeros on the end here, and then we need a third row that goes like 0, 0, and 1, like this. Okay. Boom, boom. Okay. Cool. So if we then start trying to use this thing, we need to take this thing in as a mat3, and when we multiply this thing, we have to do what we said, where we kind of convert this into something that has like an extra 1 on here, and then I think this stuff is now like a 3-dimensional thing, and probably we just want to like take the XY components from this. Yeah, something like that. So we do our xy1 times box. We do our like xy1 times box. This will give us like new x, new y, and 1. So we just have to like strip off the 1 because we're not actually using this. So that's kind of like what this is doing. And this is now kind of not just a rotation, but this is kind of like an arbitrary transform. So we're going to call it that. And let's just try to like manipulate this so that we're doing the exact same thing we were before, but everything still works. So this is now 3x3, 3x3. This is now a 3x3 matrix, not a 2x2. And if we did all this right, everything still works. It looks exactly the same as it did before. And now let's say that we want to like add in the ability to do like translations, right? So we say translate here, and we'll take in like his X translation and his Y translation, right? So we kind of do our identity matrix, which says like if you have 1s on the diagonal, it makes it so that basically nothing happens, right? Because you multiply, the first row is multiplied by X, second by Y, third by Z, you discard everything else. So this is like nothing. And then we can like tack on the stuff that we actually want to change, right? So this is like X for translation, Y for translation. And so now if we wanted to do something like replace this with a 3x3 translate by, maybe we call this angle, we'll still use angle here just for shits and giggles. This we should see it kind of like move up, kind of like move up and then reset back to 0 every once in a while. Right, so we kind of see him like shoot up to the top, and he's not resetting back to 0, which isn't good. I guess that means that our like F mod is maybe, oh, we forgot to write angle equals here. Whoopies. There we go. So he's kind of like flying off the top of the screen. Why is there only an X and Y? Shouldn't they also have a Z coordinate? Well, because we're only working in 2D right now. We have a 3x3 matrix, but the third dimension in this matrix is just a trick so that we can do translations, right? Like, we were talking about how we just throw a 1 on the bottom of this thing so that we have something to multiply by in our matrix that won't be affected by X and Y. So this is like a 3x3 matrix, which you'd think is for 3D, but it's actually a 2D matrix with an extra dimension for like math tricks. And somebody in chat will probably say, it's not just math tricks, like it's doing something in 3-dimensional space that maps to 2-dimensional space, blah, 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 but like, you know, hand wavy. Like, hand wavy, I call it a math trick. So for 3D, we'd use 4x4. Yes, exactly. Exactly. Okay, so say we want to like compose these guys together, right? We have like a translation in here, but like say we want to do a translate then a rotate. Well, we need to like do matrix multiplication. Matrix multiplication, which says like take these two boxes, stick them together into a new box. And essentially the rules are, I find, easiest to think about by this picture. So if you're trying to do matrix A times matrix B, your output of these things are like, basically you multiply the column of one matrix by like the row of another, right? So in our case, our picture would be like, A is like 3x3, right? A, B, C, D, E, F, G, H, I. And then our B is like up here, A, B, C, D, E, F, G, H, I. And our output here is going to be like, this first cell is like this times this, right? Then this cell is this times this. And the third cell is this times this. And you just do that, you iterate over all cells until you have like your final output. So we need to like implement that if we want to compose these things. So here we're like, mat 3x3 multiply. We take in one matrix, A, and mat 3x3 B. And I guess we're going to have some sort of like return value. And here we need to iterate over all of the cells. So we're going to go like, for int I equals 0, I is less than 9, plus plus I. You have like your row is what, like I over 3, right? Because we're storing row first. Our column is kind of row I mod 3. And now we need to like a way to basically extract these guys. So we probably want like, this is probably going to be like a struct vec3. A row is like mat 3x3 row, a row or something. And we probably want like a B call is like some sort of way to extract a column from this thing from B with call, right? So now we just have to write these two functions in this type. And then afterwards, we're going to say that like the output at this location is the dot product of a row with B call, where dot product is just like, dot product is like what we were talking about when we were saying like you have A, B, C in one vector, D, E, F in another. The dot product is like A times D plus B times E plus C times F. It's like you just do like element-wise multiplication and then like add all the results up together. So I guess we need to write the functions to like extract stuff. So we have mat by 3x3 row is going to return a vec3, which probably doesn't exist yet. And this is going to take in, you know, our mat 3x3 Matt and his, index. Probably row here. We also need our vec3, which is like just 3 floats. Like this. Bing, bang, boom. Okay, so extracting a row from a matrix should be really easy. It's already stored in memory such that like rows are there. So we should just be able to be like, we have some return value, we return it, and our start index is going to be like row times 3. Yep. Then we just do like a mem copy, I guess, into ret data from mat data plus start index. And we're copying like 3 floats. So like this, I think. We could also just like assign it element wise. Maybe that's nicer. There's no real reason to mem copy right now, I guess. So we'll kind of do like ret data 0 is equal to mat data at start index like this. And we'll go 0, 1, 2, 1, 2. Boom. Okay, that's kind of nice. And then in terms of column, here it's a little trickier. It's not sequential. It's like, we're going to do like, I think it's call, 3 plus call, and 6 plus call, right? If these things are stored linearly, like, you have A, B, C, D, E, F, G, H, I. If we want B, E, and H, this is like 0 plus 1, and then 0, 1, 2, 3 plus 1, 4, 5, 6 plus 1, yeah. So 0, 3, 6 plus column. Yeah, nice. And then we just need to do the dot product thing as well. So this guy returns a float, vec3 dot, and this is like A and B. And this is just like multiply the zeros together, then add in the ones multiplied together. Boom. And the 2's multiplied together. Boom. Okay. So, all of that to say, we should be able to do like a translation, then a rotation. So if we were to do translate, then a rotate, we have like our triangle here with the center here, right? So if we do the translate first, we kind of end up with center here, triangle up here. And then the rotate is kind of like, we should be kind of like rotating around this thing like this, right? If we were to do the rotation first, or sorry, the rotation first, then the translation, we would kind of rotate around this point and then translate up. So if we were going to do that in that direction, it would kind of like all be more like this, right? We'd kind of see like this. So we can kind of like show both of those. So we should be able to be like, here's my transform. Thank you, sir. And we're going to be like, transform is equal to a composition of a translation and a rotation. So maybe we're going to just kind of translate this up by 0.5. A star is born. Hey, Tupop, what's up? Thanks for the prime. Much appreciated. So this is like mat 3x3 mul. We're going to take in the transform, and then we're going to add in the rotation. So kind of weirdly, these rotations or these multiplications are done like right to left to go in order. I don't know if I like fully understand why that is, but there is something about like matrix multiplications are not transitive, I think is the word. Like A times B is not the same as B times A. So you have to go right to left to do it in the order that you want. So now we should see, okay, yeah, we are kind of seeing that where, right, we're seeing the translate first, then rotate. We're kind of seeing it rotate around the center, but kind of far away. But if we were to do it the other way, and we were to do rotation, then translation, we'd kind of see what we were saying before, where we kind of have it spinning up at the top, right, with no movement. So that's kind of hype. So we've unlocked matrix multiplication and transform composition. Wow. So far, nothing too crazy. Nothing too crazy, right? We're basically, mathematically, all we're doing is multiply adds with some numbers in a box, right? Not crazy at all. Nothing, not like the figuring out how to, like, the first person to figure out to put those numbers in a box, I'm sure had to think very hard. But we don't have to think that hard. We just have to, like, we only need to know the rules and how to, like, reason about them, right? Okay, so if only your GPU was good at that. It actually turns out that he is good at that. That's crazy. Not the GPU we made back at that one time. Our GPU was not very good at it, but the GPU in my desktop, quite good at it. Okay, so let's not commutative. One reason for right to left multiplication can be seen as abstract operator like fx. Notice the order of f and x. Yeah, okay, sure. What did I say? Not transitive, where transitive is probably something different than commutative. Commutative. How hard can it be? Just put it in a box. Well, dude, you say it like that, but like when I took linear algebra in first year university, that is just what I thought. I was like, the first year linear algebra, fucking awesome. You just put the numbers in the box. They give you some numbers on the paper, and you're like, surely these numbers on the paper go into a box somewhere, and you just put the numbers in the box, and you're like, mission accomplished, baby. Okay. I guess let's upgrade to 3D, right? So we've kind of just been like assuming, oopsies. We've kind of been making like assumptions about this window, right? Like that the triangle will be in it, right? But you can see like as you start like moving up, eventually he goes off the edge of the screen. So what determines like the edge of this screen is OpenGL kind of is working in this 3D box, right? Boom, 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 boom. And our triangle, in this example, is kind of like here, right? He's kind of like in the center on the Z axis. On the Y axis, he's kind of poking out the top, and he's kind of centered on the X axis as well, right? So this is like X here, this is Z, and this is Y, right? If we want to start working in 3D, if we move this triangle forwards and backwards in this box, it actually doesn't change at all, right? In real life, when things get closer to your eyes or like closer to the camera, like my hand is like getting bigger in pixels, right? And so kind of like the phenomenon that is like is making that happen, I guess, is like your view, your eyeballs are not working. They're not doing like an orthographic projection, right? As things get farther, they look smaller because you're actually seeing like a cone, right? So as things get farther away, you're seeing like more in the same amount of space like on your eyeball, right? And you can kind of think of that distance as like how do we say this? If we wanted to like mathematically decide how much smaller should things be as they get farther away, you can think of it as like another like high school trig thing. So you can split this into two right angle triangles. If this is my like angle of view, this whole thing, I kind of have like angle of view over 2 here, f over 2, and because this is like now a right angle triangle, you have like your rule from high school trigonometry of tan theta is equal to opposite over adjacent, right? So this is adjacent, this is opposite. And what that means is the ratio of like the width to the distance here is constant. This is a constant ratio. So what we can do is we can say, let's just scale, like as we like get farther into the world, we have like this box that we're trying to put stuff in. And basically we're just going to kind of like push things inwards into the box as they get farther away, right? And so what we need is in our like concept of a transform, we need the ability to do a division. So we're gonna like tack on another concept to this matrix. So we were kind of working, first of all, we were working in 2 dimensions before, right? So we were kind of saying that you have like x, y, 1 as like your vertex here. If we're gonna move into like 3 dimensions, we need to like expand this box to be 4 by 4, and we need to expand this guy to have a z, right? So now it's gonna be your rotation is in 3 dimensions. So you're gonna have like 3 by 3 of rotation stuff over here. You're gonna have your like x, y, z, 1 here for like your translations, and we can throw in another concept, which is that this is no longer 1. This like value, this is actually going to be the divisor for your other things, right? So you can say like, if you had like x, y, z, 2, your actual values are x over 2, y over 2, z over 2, right? And what this lets you do is it lets you in this box put 1.0 here. And it means that like when you multiply z by this thing, right, you have like 0, 0, you end up with like z as your like bottom component here. And that basically lets you do the perspective divide, right? Because now you've got like an implicit thing in your matrix that says, you know, x over z and y over z is like something you can represent through this thing. So let's start, I guess, by upgrading to a 4 by 4 matrix without doing any of the perspective stuff, and then we'll do the perspective stuff after. So we need to basically upgrade here so that our positions are in 3D, right? So here, let's add some 0.0s here in Z. Let's upgrade our V position thing to be 3D, and our transforms, we need to upgrade them to 4 by 4. And actually, before we do this, I actually kind of want to do git init, git add main.c, git commit -m, checkpoint 2D translation, because I feel like we're gonna, at some point we're gonna make a mistake, and we want to have like we want to be able to go back. Okay, so this is 3 by 3 matrix. This is now a 4 by 4 matrix. Now the output of this thing can kind of be like the transform times vec4 v pos 1.0. It turns out that opengl supports this like homogeneous coordinate, it's called. So they're already doing the like division for us, so we don't have to think about doing it ourselves. And we need to upgrade our matrix 3 by 3 here to 4 by 4. So there are now 4 by 4 things, which means 4 squared is 16. This rotation now is going to be a rotation around an axis. So this is going to be rotation, like in 2D. In 2D, you have like rotation, right? And you don't have every rotation is like basically like on the plane that you're looking at. So this is kind of like equivalent to a 3D rotation around like the z axis that's going through. So we'll just call it that. We'll say that like, you know, if we have a 4 by 4 rotation around z, how do we convert this thing? Well, we know that we have like another dimension here. And we know that like if we're rotating around z, we don't want z to change, right? So we kind of can say like, we can kind of do something like this, where we kind of put this 1.0 on the z spot, so that basically whatever z is, when it comes in, it stays the same as it goes out. And our rotation is just going to be like affect x and y now, which is perfect for a rotation around the z-axis. We need to upgrade our translation matrices. So these is kind of like going to be similar, where we kind of want like, now we're going to have a z component to our translation, I guess. And I guess we are going to do something like this, where one's on the diagonal to not affect the input, and then XYZ on the translation component here. Perfect. Vector 3 now is probably going to turn into a vector 4. I don't think we have any need for vector 3s anywhere, so we're just gonna, everywhere we have like 3s to 4s, basically. Row here are is going to be row times 4, and we have to do one more component here when we're copying the vector over. Hello, finally working in a proper language. Hey now, let's not get crazy. I think that Zig's a proper language. Okay, and then in the same world here, we kind of have to adjust this to work with our 4x4 matrix. So instead of multiplying by 3s, we're multiplying by 4s, and there's another one of them. Cool. Dot product is going to look very similar as the 3x3 dot product, but again, we just need to kind of tack on an extra thing. Boom, boom, boom. And let's see, matrix multiplication is again going to look the same. It's just that we have another row and another column to think about. So this is 4x4 ret. We're going to go from 0 to 16 now. These 3s turn into 4s, and these 3s turn into 4s. And then I think otherwise it's kind of all the same. I think. So now we should be able to like construct something that works exactly the way that it used to. So we have like a translation, but with a z component now that's going to be no movement in z, please, sir. Then we do our 4x4 matrix multiplication, and this has to rotate around an axis now, so he's going to rotate around z. But otherwise, it should look the same. It doesn't, because we fucked up somewhere. Where did we fuck up? Probably when we upload this thing to the GPU, we need to say that it's a 4x4 matrix, not a 3x3 matrix. And on the GPU side, we are expecting a 4x4. So there we go. We're back. So here's the like rotation then translation version. And if we invert these guys, we should have the translation then rotation version. Hype. Everything's still working, but now technically we're working in 3D. It's just that our 3D is only it's only affecting 2 dimensions, but all of like the math is being done in 3D now, which is hype. So let's say now that we want to rotate over the like x-axis. So we kind of want something that kind of like goes like this. We can basically copy this rotate over z axis function, but this time we're just going to replace this with x. And so in this world, we need to make a matrix that's very similar to this one, except that x is unchanged and y and z change instead. So to do that, I think you just kind of like shift these guys kind of down to the right. So you can kind of just go like like this. Okay. Now the x-axis is the 1.0 down here. Let's delete all of this excess garbage over here and here. And I think that's the same thing. You wrote xy is greater than wrote z, since you know rotation from x-axis to y-axis instead of you know right to left hand rule. Yeah, I can see that. I think that I like the idea, like in my head it makes sense as like rotate counterclockwise around an axis, but I can see your argument for doing it your way as well. But I'm gonna name them this way because it makes much sense to me that way. But I get what you're saying. Okay, so if we were then to say that instead of doing a rotation around z, we do a rotation around x, what does that look like? Like this. Okay, cool. So we're seeing like, okay, can we slow this down? So that we can kind of talk about. Okay, so we're seeing a couple interesting things here. One is that the corner of the triangle is disappearing, right? Like the blue corner is going out of bounds. And we're also seeing that there's no like perspective applied to this, right? Which makes sense. We haven't done any perspective application, but the other thing that's happening that we haven't talked about is that in this like 3D box of OpenGL land, the triangle's actually like coming out the front here, right? So he's kind of like getting chopped off like this, which means that like, and it's happening on both sides, right? Because like we are actually only representing a world that can go from -1 to 1 in z. So something we haven't talked about yet is that when we apply the perspective transformation, we also have to map all z distances that we care about into the range of -1 to 1, right? So we need to take like, some like near to far, right? Because like you're not going to render like everything. You could theoretically, but we're not going to. You're going to like map some really far distance to 1 and some really near distance not to -1 but to 0, just because that's like kind of like more convenient, and it doesn't really make a difference. And so we need to generate a matrix that does two things, right? We need to take the x and y that go in. We have x, y, z, 1 as our input, right? We need to like construct a number so that we get x over z. So z has to end up at the bottom. The z value here needs to be something in the range of like near to far. And this needs to be like this. And in reality, it needs to be near to far times z, right? Because of the fact that this is divided by z, and we're going to cancel it out, right? So to get x and y out the other end, we throw some 1.0s on the diagonal, right? That's easy. In order to get the z in the bottom component, you throw 1.0 down here, right, for the z component. We have probably x and y are not going to affect the z output, but we know we have like some values that we can put in here, and this slot here, and this slot here. We have a and b to put in here, and then probably everything else we just zero out, probably, right? And so how do we set this a and b such that it maps into this range? Well, we know that we want, so this becomes like, essentially like a z plus b over z, right? This is what we have to work with. Which means that like what happens if we plug in like near and far? So we have like a on far, z is f. So we have af plus b over f equals 1. And on the near side, we have an plus b over n equals 0. I'm going to write this in text because it's easier for me. So to do our perspective matrix, boom, we're going to call this mat 4x4 perspective. So we have an plus b is equal to 0, and we have af plus, this is an plus b over n equals 0. That's constraint 1. Constraint 2 is af plus b over f equals 1, right? Can we just like return, I just want like the fucking thing to go away. Okay, so looking at this equation, you can just delete this over n. So you just set like an plus b equals 0 because you multiply both sides by n. 0 times n is 0. Chill. Which means now we can represent one of these in terms of the other, right? We can just be like an is equal to negative b, or b is equal to negative an is more convenient. Then we can plug that shit into here, right? So we have af minus an over f is equal to 1.0, which means that surely we can solve for a here, right? We have like a f minus n over f is equal to 1.0. Then you do, multiply both sides by f, so you get like a f minus n equals f. Then you divide both sides by f minus n, so a equals f over f minus n, right? That's part 1. Part 2 is we like plug and chug back in this part to get b. So b is negative an, so this is like negative fn over f minus n, right? These are the parameters that we have found. So if we just like plug that back into the matrix we were talking about before, we should get something that resembles the perspective, the real world perspective matrix. So this guy needs to return a mat 4x4, and we are not going to worry about like field of view. We're just going to kind of hard code the field of view for now. But we are going to take in near and far. And so this looks like, we said 1.0. We said it's 1.0 for x and y. Then this is our a, so we're just going to throw an a here, I guess, and a b here. and then a 1.0 here. This is kind of what we said so far. Sir, I came here to have fun, not learn math. Sorry, it's a trick. It's a trick. This is negative f times n over f minus n. Okay, so there's one more thing that we have to talk about. And it's the difference between left-hand coordinate systems and right-hand coordinate systems. So when you have x and y, it's pretty easy. You have x goes to the right, y goes up, right? Chill. Now, when you add in a z-axis, it has to be perpendicular to both of these things. But it could go in either direction. It could come out this way or this way, right? I personally prefer this one because I think that forwards should be forwards, right? If I'm walking forwards, I go 5 steps, 5. 5's a good number for that. But everybody in OpenGL land prefers this way, right? So they kind of say that like as you get farther forwards, it's actually negative z. There are like reasons why this makes more sense, right? For it to be this way. I don't like. I guess they. Yeah, there. I've seen some cases where like graphing stuff, you know, it makes more sense to like have your scatter plot in here than like going away from you. The dude automatically picked the correct XYZ to RGB colors. He's ascended. Yeah, it's true. It's just because I've never really clued into the fact that this is because of the XYZ to RGB mapping. That's why I've never clued into that, but you're right that is why we do it that way. So okay, I personally would do this way, and we did do this way in like the weeks of work leading up to this. But for today, I'm going to do this way because it works way better with like exports from like 3D animation software and stuff like that. It'll just make our lives easier because that's the default that everyone else uses. So because of this, you know, we're talking about the idea that like as you get farther away, we're trying to keep like x proportional to z, but this direction is now negative z, right? So to keep these things proportional, we have to throw a negative sign here, right? Which means now that like these values are broken, right? And so if we think about that, we wanted like some values from a and b here. Well, like z, like the a parameter is multiplied by z and the b one is not. So if we throw like just a negative on the a parameter, I think it works out to be the same. I think. We can compare this with like if you were to just like Google like graphics pipeline on Wikipedia. They have somewhere in here they list like a perspective matrix here, and we should be seeing that this looks very similar to what we have. We've ignored width and height, right? We have 1 and 1 here. Their thing is backwards, so their negative 1's on the right side, ours is on the bottom. But in terms of like implementation here, they have far over near minus far, and near times far over near minus far. We have we ended up with far minus near instead of near minus far, so both of our answers are negated. But we did get the right answer, I'm pretty sure. Like if we just apply this perspective matrix, I think that it will look okay. What I like to do here as well is, because I'm not like 100% confident here, it's kind of nice to just do like a little Python test here to make sure that we have like perspective z test. Let's just throw in like a z near and far and like punch in the formula that we have. So we have like a is negative f over f minus n, right? And then we have b is equal to negative f times n over f minus n, right? And then we have like z times a plus b, all of this over negative z, right? This is kind of the thing that we think we're supposed to get out. And so if we just do like print perspective z test with like negative 5 near 1 far 10. So if we have like near 1 far 10, it should be like negative 1 gives us 0, negative 10 gives us 1, and like maybe everything else in between gives us something in that range. So let's just make sure that we got this right. This will also make sure that we understand, like, hello? Oh, I have to print it. True. Okay, that's really good. So this does map us numbers 0 to 1, which is hype. That's hype. That means that, like, it's very likely that this does what we think it's doing. And so we should just be able to, at the very end of this, be like, multiply our existing transform by a perspective. And we'll say, let's set our near at like 0.1 and our far at 10.0 or something. Uh-oh, unlucky, it's not working. So we take this out. Let's just make sure we do this. That's fine. As soon as we do this, though, uh-oh, no good. So why? Why? I feel like this is right. Because when I did it in Python land, oh, because the range is here, probably. So we probably need to make sure that, like, the triangle, like, it used to be, our triangle used to be in this, like, 0 to 1 box, right? So he's kind of like sitting like here-ish, right? Around 0. And now we're saying, hey, fuck you, we're actually looking this way. And so we need to make sure that we, like, put this guy kind of like where we think he should be. So let's just kind of translate him initially. Like, after we do the rotation, maybe we do like a mat 4x4 translate to like 0, 0, like -5 or something. There we go, baby. That's not behaving the way I think it should. We translate up by 1. Sorry, let's think for a second. Translate up by 1, then start rotating like this, then move the whole thing backwards. I feel like... Oh, no, it is working. Oh, yeah, it's just like, you know that picture? You know that picture of like a girl silhouette spinning? Have you guys seen this shit? Where like this is spinning both clockwise and counterclockwise, and you can convince your brain of either? I think that's the same thing that's happening here. It's like blue's close, now it's far, now it's close, now it's far. But you could also convince yourself it's the other way. It's only clockwise from your brain issue. Yeah, there's like, you can definitely like make it go the other way, but yeah, you're right. Like, it's hard. Sometimes it's hard to like convince yourself it's the other way. So this is working as expected. I'm pretty sure it's just the same problem as this. So what have we unlocked? We've unlocked perspective, transform, as well as like 3D matrices and like homogeneous coordinates. We've kind of unlocked all of these things now. The duck woman face thing is also cool. Yeah, I like that one. Okay. So we have one face now. It would maybe be nice to like upgrade this to like a 3D model instead of just like a 2D plane in 3D space, right? I think that's probably the next thing. So, we could start listing out all of the vertices of a cube, right? But there's a lot of them. Like, even just a cube, we have to draw the cube out of triangles, right? So we have to draw this triangle, then 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 this triangle, and then like ×2 for the back faces. That's too much work. I don't want to fucking do that. And eventually, we're working towards doing like a 3D animation of some form. So let's use this as our opportunity to start working with like 3D software and like importing things from 3D software. So if we just take this and we throw a little export on here, we're going to use GLTFs because they're like a common format that also support like animations and stuff, which we're gonna be working our way towards. So let's just huck a GLTF out here, and uh, the GLTF is going to, he comes with like a binary file, right? The GLTF file is like just a JSON blob that kind of says everything about the file you're looking at. The important pieces here are, let's start with like the mesh. We have like a mesh of a cube, right? The mesh of the cube is like, can we do like triangulate faces? So the mesh that's exported is essentially this, right? So he has all of these vertices in here, and also like the links between them. So he kind of has like outlined all triangles. And how has he done that? Well, we have like this meshes attribute in this thing. There could be many meshes in here, right? If we were to like duplicate this object and put it over here and like start like manipulating these guys in some way, it doesn't really fucking matter. And we were to export this now, we should see two meshes, right? One mesh per like thing that we exported, right? So if we just go like, right, now we have two meshes. So these guys, each of these defines like a mesh. I'm gonna undo this though because I don't want this second guy. He's ugly. Nobody loves him. Get the fuck out of here. So we have one mesh, and he has like basically rules about how this mesh is like read from the binary data, right? So in this guy, there's this thing like meshes has this thing primitives has this like attributes field, and in attributes he says positions of each of these vertices is at number 0. Normals are at number 1, and the links between vertices and positions, like how do we like construct triangles out of these vertices, this is at index 3. And so like what are these indices? Well, this is like in the GLTF specification defined as like look into this accessors array. So this accessors array here says position 0, so the 0th index into this thing is like I have 24 vertices, which sounds like too much. We'll ignore the fact that this is 3 times larger than it, or 2 times larger than it should be. How many vertices do we think there should be? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so 3 times as big as it should be. It's because like normals like make it so that like these guys each of these vertices is tied to like a surface. So it's kind of like because there are like surfaces that point in 3 directions, you need three vertices. Hand wavy. But this defines like buffer view 0. So we look into our buffer views, and buffer view says from buffer 0, which is a file untitled.bin, read 288 bytes from offset 0. And in that, we are going to see, I think here, it's like we are going to be reading vector 3s, so 3D positions, with component type 5126, which probably maps to float, right? We can probably make an assumption there. I believe if you look at like, if we were to look at like the OpenGL definitions, somewhere we have like GL float. I would bet that Xerox 1406, this is 5126. So that's the number, right? Like they're using OpenGL definitions for like data types. But all of that to say, there's some JSON blob. We can like extract vertex data from this thing. And index data. Now, I don't want to work with JSON and C right now. There's like kind of no reason to do that. We could and we would if this was like a real application, but I think that like in terms of like JSON processing, it's just easier for today if we do this as like a Python script. So we can kind of do like pack GLTF into like binary blobs that we know how to read from C. And we can do like def main. And we can do like if name is equal to main, we run main. Wow. In here, we're going to do like open, what do we call this? Untitled GLTF. Probably in read mode as a file. And we're just going to like JSON import this thing. We're gonna be like JSON load from F. And then we should be able to like print this thing. reinventing GLB. Well, GLBs also embed the JSON as well. So you still need a JSON reader in GLBs, which kind of sucks, right? So if we like, we can prove that here. If we were just to like write export here as like GLB, which is GLTF binary, right? Like just look, if you open this thing, you see the JSON blob in here, right? So it's not even, we would still have to do something to like, we would still need like a JSON parser in CLand if we were to do binary export. So it doesn't really help us. Okay, so we run Python, we see like a Python dictionary that represents this thing, which is hype. So now we can just start like ripping this shit. So we can go like, we know that this guy has like a meshes field. Maybe we'll open this on the other side here. So we'll look at like untitled GLTF. So we're in meshes. We're looking at meshes 0. And we are looking at like we're probably going to like look at a single primitive right now. Maybe for now we'll do some like asserts in here. So we'll like assert like len meshes equals 1. And then we'll look at like mesh 0 and we'll assume that the primitives sorry, mesh primitives, we're also going to assert that there's only one of those because we don't know how to do anything else yet. And from this thing we need his index buffer and his positions. Or let's just start with positions and we'll get to indexes in a minute. So we go primitives attributes and we're going to look at attributes position. Okay, and then like, can we just like print this for a second? Just to make sure that like we're on the right track. This is mad because probably we want like primitives 0 attributes. There we go. Okay, so we got the position 0 out of this guy. So now we're like, this is the position attribute is this. And we probably want to call this like index. We use this to look into the accesses array. Okay. And in here, we probably want to like assert the component type, probably. For now. So we're just going to be like position, attribute, component type. Let's just say like, it's probably like, it could come up later that this changes. So we're just going to make sure. And we're probably going to like assert the type as well as vec3. Okay. So now we extract the buffer view, position buff view index is position attribute buffer view, and then we go into the buffer views and we look at that. So we go buffer view is from the buffer views at position buff view index. This tells us the offset, so we're going to say like offset is equal to buffer view byte offset, and the length is byte length. And let's just like dump out this position data and read that back in CLand, I think is probably the nicest way to do this. So we need to open the thing at buffer 0. So we need like buff index is buffer view buffer, and we use that to index into the buffers array. So we go like GLTF buffers at buff index, and we look at his URI and we open that thing. So this is a binary file that we're reading as input. And can we just also open an output here? Open like positions bin, write binary probably as output. And then can we do something with that? We can probably do like F right. We probably want to like input seek, I think, probably. Python seek file. Seek offset from what? From beginning. So we want to like seek to offset from beginning. It looks like input's like a reserved word. In file, maybe we'll call it. Because it's blue. I don't know why it's blue, but it's bothering me. And then can we do like output write in file read? Can we like read some amount? Size? Yes, we were like length here. Okay, so we have a positions.bin that we've exported now, and what we should be seeing here is like a bunch of floats that represent the what is it called? Like a bunch of floats that represent the vertices of the cube, right? So if we hex dump this thing, we are seeing like 4-byte aligned things that have kind of like duplicate values. It's kind of hard to interpret these things because they're like binary data and we need to like read these as little Indian floats. So I think it's if we like read these in C land, it's going to be kind of nicer for us. So can we do something that's like load model? And in here, I guess we are going to read the content of positions bin into some buffer. Okay, so we're gonna do like fopen positions bin as read binary. I think this is file star. I think I'm just gonna assert that this is valid because I don't really care about error handling right now. Then we do like an fread, and this guy's like read into this thing. Size of thing. So this is going to be like 1 if we're reading bytes. But we can read directly into a float buffer, but we don't know how many floats there are yet. Yeah, true. So I guess we need like some buffer. Let's just start here. And can we fread into buffer? So we want, you know, size of buff, and we're reading from file F. Okay. So this is like how much we read. Is it size T? What does it return? Unsigned long. Read len equals this. Assert read len is greater than or equals 0. And then we like reinterpret buffer as floats. So for, we can call this like positions is, you know, like this. Cool. And then we can go like for int I equals 0. I is less than position, like read len over 4 because there's 4 bytes per float. I plus plus. Sure. Except actually, we were trying to read these things in groups of 3 because they're, you know, 3 positions per vertex. So can we do like I plus equals 3 here? And then we could look at like printf, maybe we do this. %f, %f, like this. Positions I plus 1, positions I plus 2. Okay. So let's load the model somewhere. Load model. And let's see what we get. Okay, so this is a really good sign, right? This means that we are seeing the vertices of a cube. Ones, and negative ones everywhere. With like, combinations of positives and negatives. What's interesting here is you're seeing the same vertex duplicated 3 times, right? And we could probably assume here that this is because these are going to be paired with normals in each direction, right? So like we were saying before, because this thing is like flat shaded, each vertex is like 3 faces, right? So we're probably seeing all 3 of these kind of batch together. And so we need to kind of like read what order we're supposed to put these things into triangles in. we saw in like the GLTF file that the mesh had this thing called like indices, and this basically means like we are going to give you some points, right? But how we stitch those points into triangles is not just like doing it in order. We're going to like select them in some arbitrary order, and that's so that you can kind of like reuse vertices, right? Because really, this vertex is connected to one, two, three, four triangles, but we only actually have to duplicate it 3 times because these two share the same normal, which means that these 2 triangles share like the same like exact vertex here. Right, so that's why they do it that way, is because we kind of like fold down the amount of things that you need to have in the world. If this was smooth shaded, you could get away with 8 vertices instead of 24. So let's, I guess let's first kind of implement something that uses an index buffer in CLand. Then we'll try to use like the one that comes with the GLTF. So let's upgrade our triangle example here, wherever the fuck it is. Can we upgrade this into a plane, like a square or something? So that means that this kind of gets like negative 0.4 here. Okay, so if we render this right now, what do we see? Cool. So we're seeing like a triangle that's kind of like right angle-ish. I think this actually should be negative 0.6 and 0.4 actually. I think that looks a little bit more like a right angle triangle. Okay, cool. And then let's adjust the colors here so that anything that is like, let's just do 0.5s everywhere actually. I think that's nicer. And then let's kind of use red and green to represent its like x and y axis. So this is negative negative, so 0 0. This is positive negative, so 1 0. This is negative positive, so 0 1. Okay. Hype. Cool. And now we just have to like add in the other triangle. So if we were to add in the other triangle without index buffers, we would kind of do something like this, right? Where we would go, first of all, we need to update this guy. Can we do this? I don't know. We would say, okay, so we've got top, bottom left, bottom right, top left. So we need to discard bottom left and replace it with top right. So we kind of just take the negatives off this guy and assign him 1 1 here. Now when we render this thing, we still don't see anything because we actually have to tell OpenGL, excuse me, sir, there is more stuff there for you. More stuff for you to look at, which is probably like here when we draw the triangles, we say there are 6 points now, not 3. Right? So now we have our little square, but we haven't done this with like index buffers. We've done this by duplicating vertices, right? So what we actually want to do is we want to kind of just store these 4 things and store indices into this stuff, right? So if we were like uint32t indices, and we're gonna have 6 of them for 4 vertices, this is gonna look like 0 1 2, and then the next triangle is gonna be, I think, 1 3 2. Let's think about this. It's boom 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 boom. This is negative negative. This is 0 1 2. It looks like we're going counterclockwise. So if this is 3, we want to go 1 3 2 to stay counterclockwise, because like the order of this like kind of matters sometimes later. I don't think we have to think about it too much right now, but like theoretically the winding order is important. So the order of this is important. Okay, so now we have to unlock the new concept called index buffers. So we were kind of talking about at the very beginning of this stream, we were talking about how when you like load data into OpenGL land, you have like data, which is these like buffers, and you have kind of like definition of how to use that data in OpenGL land. How do you calculate a positive versus negative winding order? What do you mean calculate? Oh, like how do you tell which way it's wound? I don't know. I'm sure there's a way to do it. I think we thought about that when we did our like GPU, our like fake GPU implementation, but I don't remember the math. I don't remember. Given 3 points, how do you know if it's clockwise or counterclockwise? Yeah, I don't remember. I'm like looking at it visually, but like I'm sure there's a way. Probably you like cross product them Yeah, you probably do like you take this vector and this vector, right? If this is like your points like 0, 1, 2, if you like take the cross product of these, you, like whether it's like positive or negative probably tells you what the winding order is, probably. There was some math that claimed to do it, but my simple brain didn't work and I got distracted before I got it working. I'm pretty sure it's just cross product. Pretty sure. Um okay. So yeah, so in OpenGL we have like definitions of like there's like kind of like data positions, right? Positions. And then we have like now we have like this new data indexes. Right? And then we also like theoretically this is actually positions plus color is kind of what we have over here. We kind of have like this is all gets all tied into like this like vertex array object, which is kind of like how do I interpret this data, right? So here he kind of says like positions in buffer 1 at like at stride of like 5 floats apart, but like the first 2 are the ones we care about, right? Then we have like color is also 5 things apart, but we're actually looking at like 2 to 5 instead of 0 and 1, right? We can just kind of tack on here some like index data information, right? So here we say like, give me a buffer to work with. You know, we can go like element buffer object, I think is what they call it typically. We can kind of like create a buffer, stick it in EBO, and then we bind this. We say like, hey, I'm going to be doing some like buffer operations OpenGL, and just so you know, if I do anything related to the element buffer, do that with like EBO, this identifier, which lets us do stuff like say, let's upload some data to this thing to the element array buffer, which is like different than like data buffer. I don't really know why, but this is kind of saying like, hey, there's some index buffer, and we look at indices like this. Okay. Then when we start setting up like our definition of how to like interpret the data in here, we should be able to just be like, I think if we just make sure that this is bound, I think it's fine. You might have to enable something here. Yeah, I'm not entirely sure. Vertex, learn OpenGL, element buffer. I think that you just have to bind it, but EBO. Here we go. Okay. Can we just like look for an example? So they bind it. Yeah, they just bind it. And then I think it's fine. Okay. So then instead of calling like draw arrays, which says like loop over all of the positions of this thing, we use a different call, GL draw elements, which says, hey, use a level of indirection, look at the element buffer, and use that to figure out which things from like the position buffer to look at, essentially. So we're still going to be rendering triangles here. And then what are our other parameters? It's like count, so how many things? It's still 6 indexes. Because we have 2 triangles we're trying to draw. The type here is like, you could have your indices as 32-bit ints, 64-bit ints, 8-bit ints, right? It like really depends. So here we just have to tell it, hey, interpret this stuff as 32-bit integers, and then what is this? Maybe this is like an offset or something? I think you just write 0 here. There we go. So we've got our little square thing back, but now he is using the index buffer, which is kind of huge for us. So we've unlocked like index buffers. Huge, huge for us, which means now in our Python script, we should be able to start like, we should be able to like extract the indices, the index buffer that he has, and like spit it out in like an adjacent file. So maybe we're going to do something that's like dump buffer data, maybe, and we're going to dump it at some path. And with some offset at some length. And maybe we're gonna take in like, maybe we could like dump accessor. That kind of might make more sense. So we're gonna like take in the GLTF, accessor index, and the path, and then probably we can kind of take like all of this stuff and split it out. So here maybe we can say like expected component type, expected type. Then we can kind of do like expected component type here, expected type here. Okay, so this is all the same. Our output file is now path. Otherwise, it's all the same. So we can kind of now just say like dump accessor. What are our inputs here? Position attribute index to positions bin with 5126 and vec3. Okay. And now we should be able to do the same thing with like the index attributes. Untitled GLTF. Okay, so now we have like indices here, which is from primitives. Primitives 0 indices. And this can go into indices. And then what are our expected types here? 0, 1, 2, 3. So we're expecting scalar, true. And of type 5123, which we should look up what that is. But we'll figure that out in a minute. Okay. He's not happy? Why? Did I spell indices wrong? Yeah, I have an extra I in there. Okay, cool. So now we have indices and positions, hype, and if we were to like hex dump the indices, do they look reasonable? Maybe if they're 2 bytes each, we're looking at like 14 or something, 7, 1, 6, 15, except that would be big Indian. No, this would be little. Yeah, so they're probably 16-bit integers here. Probably. Okay. On the C side, we should kind of like extract out this like load file shit. Because we're going to be doing this a lot probably, right? So let's do like load file into buffer probably. Let's kind of like try to make one shared buffer for everyone. And let's kind of like say that there's some like buffer that we have that has like data as like a, you know, data and len. And then as we load stuff, this buffer will like shrink. So we kind of go like this, and then I guess we probably just like return the shit. We probably have to close the file too. I think we just didn't do that before. Okay, so this is gonna be buff len and buff data here, pipe. And then at the end of this thing, we like adjust the thing. So we say like our data plus equals read len and buff len minus equals read len pipe. And then we should probably like return the thing that we read. So this is like the old data plus the read len, boom. Then we can return this thing. Okay, so now our load model should be able to be like, we probably need to write what the file is that we're loading, surely. Okay, so now we should be able to be like, give me a buffer and we'll read from that buffer. You know, he's gonna like look at buff data and 496, probably something like this. now we are like positions buff, I guess, is like load file positions bin like this. Okay. Okay, so does this still behave the same way? So we still are reading positions data well, which is hype, and now we should be able to read like index buffer in kind of like the same way, and we should be able to be like, first of all, what was the type we saw there? Indices was 5123, so 654. It's unsigned short, I think. So I think it's like this. We have some indices at indices data, index buff data. Okay. Then we loop over index buff len over 2 because it's 2 per, I plus equals 1, pipe, and we're going to print out the index of the thing. Kind of like this. Okay. So this looks promising. We are seeing like values between 0 and 24, which is what we were expecting. And it looks like we're kind of like sampling from like kind of all over the place in this guy, which is again what we expected. So we should now be able to create like a vertex array object out of this stuff. So like here, when we were doing our like generate some buffers, bind some data to it. First of all, if I copy paste that down there, nothing breaks, right? Yeah. So we should be able to like take all of this stuff and put that in load model. And we just have to be very careful about what we're binding here. So we create a vertex buffer. We upload no longer size of vertices. This is going to be positions buff len and positions buff data. So this is the vertex data. Then we create our vertex array. We set this stuff up where we no longer have colors associated with this thing. So we'll kind of come back to that. But for now, we just leave that disabled. And then our index buffer is coming from index buff len that we read and index buff data. And then when we draw elements, we're doing unsigned short. Okay, this is showing nothing, but it's likely that our fragment shader is broken because we disabled the color stuff. So can we just kind of unconditionally do white? Unlucky. Unlucky. So I guess we're also not using this model because I'm a dumbass. So we do have to like return probably the vertex array. So let's kind of like disable this thing and then return it. So we need to say like, we loaded some data. Here you go. And then can we just comment out what we were doing before? Now we are going to use the data we loaded. Promising. I don't know why we're seeing one triangle instead of lots of triangles because we're only rendering one of them. So here we probably need to return not just the buffer, but like how many faces there are. Probably. Right? So here we're gonna have like the the vertex array object as well as like num indices, right? That seems fair to me. So we return the vertex array and then also index buff len over 2 because it's shorts. So now can we do here? This should be like the thing we loaded is now actually a struct model, load model. Hell yeah. Here we use the model vertex array object and the model num indices. Okay. Still not great, huh? Are we using... It's interesting that we've managed to get one triangle. That's pretty strange to me. I wonder if we're like accidentally still using this stuff. I assume we're not. Oh, and then we're also the vertex definite. The how the data is laid out is changed. So y over 2 isn't already u16. Here it's a u8. The buffer, this is like buffer length, not like data length. I'm pretty sure. But here, okay, we need to think about this. So this is now 3D vertices. So this guy should be saying, hey, sir, I am uploading a vector 3 of floats, and they are 3 floats apart from each other. And their initial position is 0 bytes offset from the start. Yes, I think that's right. There we go, baby. There's our fucking cube. There's our fucking cube. That's sick. That's sick. So here, now we're getting like some very strong indication that like perspective is working, and we've like loaded 3D model from GLTF, which is quite exciting. So let's try to make it so that we can kind of like see some stuff from this guy. Well, let me think about where I want to go next. It's 2:30. We could do like lighting next, but I think that if we're trying to do like animations, it might make sense to do bones next. I think lighting's pretty quick to do, so we might as well just do it. Fuck it. Okay, so this cube is gonna have a color, and like in 3D land, it's kind of nice to be able to like see like definition of edges, right? Right now we're kind of just showing everything as white. So what we do is hand wavy, hand wavy. If you have like the sun, right? The sun's over here, right? Really far away. And so he's really far away. Earth is like way the fuck over here, right? And so like all rays of light that hit Earth are coming in what is like a very, very narrow field of view. Like this is like small as fuck, right? So from the Earth's perspective, you can almost consider like all light from the sun as perpendicular with each other because this angle is so small, right? So the difference between the angle of anything from the sun is like it's not enough to worry about. So if we were to make like the sun, you can kind of imagine that you have like a thing in the world and you have like light coming in, right? And you can like look at this and you can kind of say like, okay, this face, bright as fuck, right? These faces, probably not lit by this. And if they were like, if they were kind of like on an angle, right? If you had something that looked kind of like, excuse me, sir, I want to use the eraser, thank you. If you had something that was like kind of like this, it's like these faces are lit like kind of a little bit. This face is lit like not at all, and this face is probably like bright as fuck, right? Hand wavy. Now, in the real world, like there's like stuff, right? And like light will like bounce off this, and like the back a little bit, and bounce off this, like the back a little bit. And so like kind of hand wavy, if you average out all the light bouncing, there's probably some kind of like if you look like around like your room in your house, like the windows over there in my apartment, and like the rest of the room is kind of like hand wavy, like constant light, right? It's like where the sun is not like directly getting through the window, it's like you either have like stuff that's lit by the sun or like not. Hand wavy, we're glossing over details. It also doesn't have to be that accurate, right? So you can kind of like split these two concepts into like ambient lighting and like diffuse lighting. Diffuse would be like the stuff that's like the light is hitting directly, and ambient would be like kind of just like the brightness of the room in general. There's also like specular, which is like me as like the viewer. Um, if like my eyeball is here, I've got some eyelashes, and I'm like looking at like this surface, and the sun is like coming in like this, and these like kind of like reflect. It's gonna be like really fucking bright, right? And like it depends on like my viewing angle and the sun's angle normal to the surface. So there's also like that. That's called specular. I'm just gonna ignore that for now because I don't want to think about it, and it's not. I think that like in order, if the goal is to kind of just like see stuff a little better, then you don't really need specular. I think diffuse and ambient is like plenty good enough. Um, and so in order to like calculate kind of like how much the sun is like hitting this thing, we need like normal data where we can basically need to know like which way are these faces pointing, which lucky for us is something that the GLTF file gives to us, right? So if we just like go in here and wherever the fuck we were looking at like position, we can kind of like do attributes position here. We can just copy paste this and look at like normal, I think. Yeah, normal, and write it to normal's bin. And otherwise, this is like exactly the same. So if we run this, he's happy. And in main.c, we start looking at like normals buff. There's a good chance we stack overflow here at some point, right? I guess fread will. We're clamping the read in load file to the length of the buffer, so eventually we'll just run out of space, which is fine. We won't like stack overflow or like overwrite or stack and do weird shit. So we have this like normals buffer now. Let's just kind of read this thing and see if we can interpret it. So I actually just deleted something that would have been useful there. So we can kind of loop over normals, 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 normals. Yeah. Okay, so we see that our normals, they kind of look very similar to the positions, except they're going to be like offset by, they're like perpendicular to the buffers we were seeing before in some way. But we have like normal data. Oh, sorry, actually, maybe not. Maybe I was a little too excited there. Normals. All right, let's try it again. Here we go. So this guy's pointing straight in Z, straight in Y, straight in X, straight in Z, straight in Y, straight in X, which does line up with kind of like how this cube looks, right? Straight in Y, straight in X, or yeah, there's like axis inversion going on as well. They Blender has Z up, we have Y up, so there's kind of confusion there, but looks like it's right. And so we can probably like feed this data into the vertex array. And so do we have that picture still? This thing? So we can now just like slap another thing in here. Normals. Right? And then in our like definition of how OpenGL reads this stuff, we're just like read normals from here. Right? Hype. So we can do that. We can do that. So we just say we create a multiple vertex buffers here. So we'll call this vertex buffer is going to be renamed to position buffer. Okay, we're gonna kind of like reorder this stuff a little bit. So we're gonna define our like we're gonna make our definition of how to read the data. We'll bind the position buffer and say read positions from this spot. Cool, right? Now we can say like, okay, let's make a normals buffer. Normals buffer. Boom, 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 boom. Boom, 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 right? And we can say, hey, the stuff that is bound now, assign that to the thing at location 0. These are still going to be 3-dimensional float vectors, so this is all fine. And we should be able to just go into our vertex shader now and say vColor is now vNorm. We're going to output probably the normal to the fragment shader for now. And can we do like absolute value of norm like this, just to kind of see if it like looks reasonable? He's unhappy. So that's not good. We must have done something wrong. Okay, so we know that the hold on. Oops, I was like in like a file manager that whole time. Let's just Nick shell again. Womp 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 womp. All right, yeah. So this is still showing anything, but we know that the normals are valid, right? So it's likely that this is like a mistake with how we're uploading the data. Let's go back to the fragment shader and try to only show 1.0 again, just to make sure that we didn't like accidentally break the cube rendering, which we did. So that's interesting. It's possible that this stuff just isn't compiling, by the way. Yeah, it probably isn't, because we actually just haven't fucked up our vertex shaders yet, but we should probably fucking check that they compile properly, which is easy to do. We just need to do like compile shader. Boom. So let's take in like the shader type, which takes in a GL enum, and the text here. So this gets this. Okay. Then when we compile the shader, we should check the compile status. GL get shader IV, I think it is, with like GL compile status. Nice. From vertex shader, and this guy wants like a int output. And then we go like if status is equal to 0, if not status, probably. Can we printf? Uh-oh. I think this is how we check if it succeeded or not. And then here we should be doing like, this is compile shader, vertex shader text. Oops. With GL vertex shader? Yeah. And fragment shader is the same thing with fragment shader text and fragment shader. All right. So he does say uh-oh in here, which is good. Now we should try to actually like get the information of like what went wrong. So can we do like, we have some character buffer where we're gonna read the status into. It's like get shader info log. Nice. 496 is our buff size. Length is like how much we actually read. So len, and then we read into buff. And then we have like, what is the type of len here? GL size I len, and then we just print f whatever we got. So some string of this length, probably followed by a new line, and then we pass in len and buff. There we go. Color undeclared, vcall undeclared. Hype! So now we can go back in here and we can fix our shit. So it should be like norm is v norm. Womp. Let's go. Okay, so we're back to white cube, and then can we show the normals again like we were trying to do before? Okay, so semi-good sign. We are seeing like colors that represent the correct axes, and we're seeing them rotate. He's not actually reading chat, he's looking at something different. I just don't care. Okay, so let's spamming question marks and being like, why don't you answer? It's because I don't fucking want to. Is the answer. I don't really it's just I'm doing something else right now, you know? It's my stream. I get to choose. I get to choose what we talk about. Not gotten out if he's talking to me. Get fucked. Okay. So let's fix the depth testing here. So what happens here is like each triangle, like from perspective of camera, is like somewhere in this like box, this OpenGL box. Some of them are kind of farther back, and some will become like blocked by others. And so what happens is after all of our like projection is done and all that shit, we OpenGL can ask the GPU to only render the closest thing, right? So what'll happen is as we are going through the vertex shader, he'll like write down in some picture, like, hey, this triangle was like at 1,000 meters, right? And then he'll get like another triangle that's closer, and he'll be like, oh, if what we drew is like less than 1,000, actually this is going to be like 1.0 because we did our depth mapping, right? Everything's going to be in the range 0 to 1. So this is going to be like, oh, I'm at 0.1 now, so I'm going to color this on top. And so he's just like, we can ask him to like preserve that part of things. So we can say like, or we can ask him to like basically only render if it's in front, instead of just like whatever fucking order you happen to render the triangles. So we can say like GL enable GL depth test, and we should also clear the depth buffer between frames so that he's like not trying to like remember what was there before. And that's looking real good, baby. Look at that shit. Look at that shit. Okay, so now we have normal data. And so let's kind of go back to this idea about like the sun, right? So we can kind of say like, at like, maybe we'll just make it constant. That's kind of easier for me. So we can go like vec3 sonder is going to be like probably like straight above, maybe like kind of pointing down, right? Kind of something like this. And then can we do something that's like let's calculate the angle between our normal and that. So our normals are going to be pointing up, the sun's going to be pointing down, and so we can kind of like calculate like the angle between those, one of them inverted. And so if they're like really aligned, that's good. And if they're like not aligned at all, that's bad, which is like cosine essentially, which is the same as the dot product. And the dot product is just like an essentially like cheap way to calculate cosine because you just only have to do multiply adds. So we're going to do like, dot norm with the negative sonder. Sonder. That's like a word, right? Shut up. So this is kind of like the like diffuse amount, right? And we also need like the ambient amount. So we can kind of just say that there's like some ambient light in the world, maybe like 0.8 of it. And then we should just be like ambient times diffuse times like some color. So let's just do like white for now. And I think that should do something sane. Looks like the ambient amount is not coming into play here, or this is backwards. So if we were to just do like ambient, no diffuse, that looks like that, which makes me think that the dot product is going to sometimes be negative. So can we clamp this from 0 to 1? Let's make sure that we have the clamp arguments right. Min and max. So maybe we want like, we want like the maximum of this and 0. Actually, we don't want to clamp it to 1. Okay. Oh, this should be ambient plus diffuse, not times. I'm a dumbass. Norm is in model space still? Yeah. So this is like if we were rotating the camera and not the cube. So we do need to fix the fact that like we kind of want it so that the sun is always like above, right? And it's not the case. So we need to like basically just adjust the normals that we're getting, right? We're kind of like applying them in model space. This transform is like model to world and perspective transform, which is like a little bit confusing. So can we like call this like viewport transform, and then we'll call this world transform. We'll kind of like split the concept of like perspective from everything else. That allows us to kind of say that we'll take the position of this guy, we'll do the world transform first, you know, basically like position this cube in the world, and then position the world according to our camera is kind of like how you can imagine this. This allows us to basically take like the rotation component of the world transform and apply it to the normal. And now all we should have to do is like split those two things. So we have this should be world, this should be viewport. And we'll kind of say that the cube is moving around the world. We could also do like rotations like of the camera around the thing as something as well. But projection is the typical terminology for world to clip space. Viewport is sometimes used for clip space to window. Oh, that's fair. Well, this is my stream, and I get to choose what words I use. You can't stop me. But you are probably right. I just don't want to. I don't want to think about it. Okay. It is, yeah, I probably shouldn't be. Yeah, future me is going to be pissed. True. That's classic, though. I feel like anger is like the best way to like solidify knowledge, you know? That's not working. Transform undeclared. True, because this is a viewport transform here. Okay, so we can kind of see this looks kind of weird, but we can see that like as the thing points up, we're seeing more of it. If we kind of point the sun a little bit backwards in Z, that might, I wonder if we'll see something a little bit more sane. Or maybe we decrease the ambient amount. Yeah, there we go. That looks pretty good. It's probably like the 0.8 to 1.0 was just like a little much. So that's pretty cool, right? I think that we've kind of unlocked like diffuse and ambient lighting. Plus like normal mapping, kind of. All right. So I guess next up would be let's try to make this like a guy, right? I think that's probably the next step. So let's do like a get add dash u, get status. What's like in here that we probably want like pack GLTF pi. I guess we don't have like a Blender file to work with right now, so that's fine. Let's just say like checkpoint 3D rotating cube with lighting. Okay. So yeah, let's make a little guy. So what's he gonna look like? A cube. We'll call him Cube Man. Call him Cube Man. And so let's give him like, you know, he's got like a head, and you know, we don't have to get like too fancy with this. Let's just kind of make the equivalent of a stick man. So what do like legs look like in 3D? Also, we need to make sure that we get his like forward direction kind of reasonably, I guess. It doesn't really matter, I guess. So you could do like a loop cut like this and extrude his legs from here. Right, that's an option. But I don't think that you want all of that geometry up top. Not that it fucking matters. But I think what probably makes more sense is to do like a loop cut here and then start like extruding here for his leggies. Right, so we can kind of make it so that like maybe like this needs to get rotated around this axis by like 90 degrees, and then this probably wants like the same, and then probably we should make it so that like he has like hips of some form. So like I guess like probably these vertices probably like come in. Yeah, that makes him look less fucking weird. This is horrifying. Shut up. It's fine. And then he's got like bell bottoms on, kind of, huh? And then we probably want to give him like knees. He's the bee's knees, dude. Okay. Hell yeah, dude. Okay, let's give him some armies. So we'll just gonna womp. Womp 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 womp. Okay, sure. And we'll give him some elbows as well. All right. Doesn't really matter. Okay, let's save this as like our little guy. Guy. And so I guess I actually kind of want to like round him out a little bit. I think that's kind of nice. So you can just like subdivide. No neck, no torso. Yeah, I don't really give a fuck. I don't give a fuck. You can't make me. And that's actually probably fine. We can also like smooth shade him. And maybe we want to subdivide him a little bit more to give him a little bit. Oh yeah, look at that. That's a fucking guy, dude. So can we export this now as our untitled GLTF? And now if we import this guy, unlucky pack. We have to run our Python script. No. Oh, I didn't run it. That's why. So it looks like we need to apply modifiers when we export to make sure that like he turns into all of our like subdivisions are getting applied. Data mesh apply modifiers. Here we go. No, that's not good. What if I hit like apply here and then just export GLTF? Pack. GCC. That's not good. That's not good at all. So why would this be different? Is he too big? Before the cube was kind of centered around like he was kind of like a different size before. Bum 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 bum. I hate it here. Looks mega smooth. What are you talking about? It's an SCP. Not enough buffer space? Oh yeah, that seems kind of likely. It's weird that it's not kind of falling over harder than that, but I guess we could do like assert readline is greater than 0, not greater than or equal to, and then we're crashing. Yeah, good fucking call. Thank you. It's so sick when you guys are in the chat. Look at SCP-103 and tell me that's not what you made. Fine. Ew. Don't make me ew. Why did you make me look that up? I don't like that I did that. Okay, let's take in the buffer here, and then we can kind of say like low like buffer buff is gonna be like malloc 10 megs. Something like this. And then we can just pass in the buffer here. All right, let's try that. There we go. Sparrow runs next to us. SCP is secure copy. I was thinking about SC like secure copy there. Okay. Wait, I missed it. What did you fix? Yeah, you were busy fucking looking up that demented motherfucker, dude. It was just like I was the file size like I was reading all of the vertex data into like a 4K buffer, and then since I added a bunch of vertices, it like wasn't enough room. Okay, let's like change the rotation here. Can we like rotate him around like the y-axis, which I don't think we have a function for? So y-axis is like this needs to look similar, except the y-axis is unchanged, so this becomes C and S here. And then we can kind of spin around him or something. So let's kind of like look at him like slightly from above, and then rotate around Y, and then translate him back away from us. Okay, let's kind of even like send him like, we don't have to send him so far. We can hold hands, and then we can even send him like maybe even a little farther down from us. All right, that looks pretty good. That looks pretty good. All right, let's give him a skeleton and give him some animations. I'm not gonna let's not get too crazy. We don't have to do anything too impressive here. Um, armature. Okay, so let's just try to make this like, we'll give him like a spine, right? Can we go transparent so I can see this shit? We'll give him like a spine, and maybe we'll even give him like a head. You know, why the fuck not? And can we like give him like an arm that maybe kind of starts here and like goes to his elbow maybe, and then like another one? Uh-huh, sure. Oops, all of this is kind of in the wrong spot, isn't it? Isn't it? Okay. Let's give him another arm, I guess. Add, you know, like, something like this. Boom, boom, boom. And then we could give him some legs too. I guess we could just give him like a little waving animation, in which case he doesn't really need legs. But fuck it, let's give him some legs. Okay, so it's gonna like this, like this, like this, and then we do another one, another one. Okay. Well, hello. Here we go. Here we go. Here we go. Here we go. Cool. So let's make sure that everything is kind of parented correctly. So everybody's going to be connected to his pelvis, I guess. Uh-huh. Uh-huh. And otherwise, that's looking about right. So let's set this up so that this guy is kind of, parented to this guy with automatic weights. And we can look at like, what the fuck did it do here? Like, are our weights like kind of reasonable? So how is it deciding that these bones should affect his body? And I would say that's pretty reasonable, right? So each bone here is kind of heat mapped to like the correct area of the mesh, which is kind of cool. And maybe we just make a simple little animation initially, where maybe we'll just make him wave. I think that's probably fine. So can we like go into animation mode? I guess we should do something that like, yeah, we'll just make him wave. I don't want to get crazy here. So let's make like a 20 frame animation, and let's just like only move his right arm because I just really do not give a fuck right now. So I guess maybe we'll make it kind of so that his like left arm is like not fucking weird. Do you guys like have this problem where you like just don't know what to fucking do with your hands all the time? Like we'll put it in his pocket like a fucking awkward piece of shit, right? And then we'll kind of give him a little wave. So we'll kind of checkpoint these guys. I guess we want to checkpoint their location, rotation, and scale. It seems reasonable. And then maybe like 5 frames in, he's kind of... I guess maybe this will just be a 10 frame animation because I don't really think there's much more needed than this, to be honest. Ew. What the fuck? Did I not copy everything? Oopsies. Why does it look like that? Is it that this needs to be at frame 0? Yeah, there's something fucking weird happening here. What the fuck? Look at the bottom right. What, it's like resetting, but it should be like exactly the same. Oh, this one, bone 3 maybe, is not being copied correctly over. There we go. There we go. Okay, cool. There is our animation. It doesn't have to be more fancy than that. All right. Boom, boom. Okay, so like, what's like the first thing that we need to do here? Probably like load the bones, right? Yeah. And okay, so let's look at like the new GLTF. Um, like what are we seeing here? We have like a bunch of nodes in this like top level node array, right? And each of these bones, oopsies, each of these bones has like parameters for its like default position, right? So if we were to like open this guy up before we run the animation, he probably has like his like we're probably seeing this. We might be seeing this. One of these two things. I don't know which one. Wow, he's so handsome. Yeah, he's like paint me like one of your French girls. It's probably the T-pose. You're right. And so these guys have like a rotation, translation, and scale in like local space, right? So what happens is like you have, you know, one bone like this, right? And if you have like another bone here, you're gonna kind of say that this is like a 90-degree rotation plus like the offset from here to here, right? Plus this translation. But for this next bone here, this has no rotation and only a vertical movement from this guy, right? Because once you've done the first rotation, the next thing is like continuing along that existing rotation, right? And that lets you kind of like rotate kind of like your whole arm at once without having to update the rotations of every single bone as part of that. So that's kind of like what we're expecting to see here. And so we have to kind of map the children. We have to figure out like the parent of each node. They map it as children. I think that's probably more efficient to map as children, but it does mean that like you have a one-to-many mapping, which is just like a little bit more of a pain in the ass. I think that we can represent this as like a single parent per object, because I think that the GLTF spec says that objects have to have one and or 0 or 1 parents. I think that's what it said. At the very least, our bones do. So we're kind of chilling there. So I think step 1 is probably to parse all of these nodes and output the rotation, translation and scale of each of these guys. And so like, how do we want to represent that? We can probably export from Python land as like one giant nodes array, I think. So we could go like GLTF nodes. And we could say like for node in nodes, can we like basically just write out like position is node. Sorry, this is gonna be like translation. Translation, is that what it was? Asset untitled GLTF? Yeah, translation, rotation scale. Okay. Scale. Rotation, scale. Okay. So translation, rotation, scale, but sometimes these won't exist. So we'll say like if translation in node, else his translation, his default translation could be 0, 0, 0. I think that's a fine default. Rotation is a quaternion. So we'll kind of get into like what a quaternion is a little bit more, but the default quaternion should be 1, 0, 0, 0. Actually, I lied. 0, 0, 0, 1. We'll get into why later. But just trust me for now that that's like kind of no rotation. And scale is if scale in node, else the default scale is like no change, right? So no change in X, Y, or Z. And we can just kind of like take each of these nodes and just like pack them as floats into a like nodes bin. Sure. So binary write as f. Oh, Python backseating node.get. Oh, that's way better. That sounds way nicer. Let's do that. If only I'd known. So this was 0, 0, 0, 1, and this was 1, 1, 1 for scale. Okay. Okay. So we probably want nodes.bin. We probably also want his parent to be in here. So I think that we want to like rip nodes, and they store children, but we can kind of say like parents is equal to like uint 32 max. For this in nodes, yeah, and then for each node we like look at his children, and then you said to use like get children with a default of nothing. For each child we can say like parents child equal to I, which means that we need I, which means we write enumerate here. Okay, so this like populates a parents array here. So then we can iterate all the nodes again. We have like the parent now. Which means that we need I here and enumerate here. Okay, and now we can just like pack all of this data into the structure, right? So we can go like, how do you do this again? Python write like binary float data or something. Like, what's the? I think you have like the struct module. Oh, they have two file. This is what I've seen before. Alt F4, thanks for the tier 1, much appreciated. Thanks for talking about it. Oh, no worries. Of course. I feel like I've seen this before. So let's do that. So this guy's kind of like a module who's kind of meant for like interacting with binary data, binary C data. So we can say like we want to write out, you know, this many floats. We want to go like f write whatever the fuck this thing says. So we have pack this many floats. I think you want to specify that they're little endian, if I remember correctly. Struct module Python. Little endian, yeah. And then f is probably float. This is like a printf format string for binary data. Yeah. So we're like, give me little endian floats. We're gonna write out little endian float this many times, and then we're gonna splat that shit in, and then I guess we just do the same here for rotation and scale. Okay. Right, so, and then we also want to write out the parent, but the parent is going to be an unsigned integer. So capital I. And there's only one of them, so it's just like this. Okay, so this should give us like node data that has translation, rotation, scale, and parent in a way that we can like interpret from CLand, I think. He's mad because bad character. Oh, because these need to be like this because they're multiple characters long. Bad char in struct format. Am I wrong? I thought that's how you did it. Yeah. Wait, what's the problem? Okay, let's only do. Okay, so that works. So it's probably the times length thing. So maybe the little endian just comes at the very beginning. So we probably want like this plus f times this or something. Does that work? Yeah, that works. Okay. Yeah, not sure if you can specify endiness multiple times. It does look like that's the problem. Does look like it. Okay, so now what? We want to like look at nodes bin. And what are we hoping to see? We're hoping to see like 1, 2 translation, kind of here, rotation, scale, parent. Okay. Parent, probably parent down here, as the last guy has a parent of nothing. Right, so this last guy has like what looks to be basically like identity. It's hard to interpret like binary float data, but it does look kind of right. It looks like maybe, like not guaranteed wrong. We're seeing some patterns. So can we try to load the nodes here? Where are we? Load model. So in here, let's look at the nodes buffer. And what are we gonna do with this stuff? Let's just print it for now, I guess. So I is 0, I is less than nodes buff len over like node size, probably. We have to like figure out what node size is, but this is probably something that's like, we have 3 floats for translation, 4 for rotation, we have 3 for scale, and then 1 uint32 for parent. So this is 3, 6, 10, 11 times 4, right? And then this is b semicolon. Okay. That sounds about right. So then can we try to read this stuff? So can we do like nodes float is nodes buff data, and then like uint32 nodes u like this, and then can we say like, can we just get like printed? Maybe we like put this stuff somewhere, probably, right? So maybe we have like node here has like a translation. Yeah. Oh yeah. Rotation and scale. Pipe, and then also parent. Okay. So then we can have like in here, we can have like nodes, you know, struct node star nodes, and then like num nodes probably is probably the play. That seems reasonable. So here we should know how many nodes there are. This is gonna be like nodes buff len over node size. Good afternoon. Well, yo, what's up? What's up? Long time no see. Glad to have you back. Okay. And then like what? I guess we like allocate for now. Yeah, fuck it. We'll just leak the memory. I don't really give a shit. Struct node star nodes is this, and we're gonna do like num nodes times node size. Hype. And I guess then we're gonna be like nodes I dot translation 0 is nodes float. Oh yeah. At I times node size. No, at I times. Ooh. I guess we also need like a elms per node is gonna be 11, and then we go elms per node like this. So then we can go like elms per node times I. Yeah. And then translation 1 is this plus 1, 2 is plus 2. Then we're on like rotation. So 0, 1, 2, 3, 3, 4, 5, 6. Then we're on scale. So 7, 8, 9. And then we're on parent. Yeah. Yeah, 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 yeah. All right. All right, all right, all right. Cool. So then we should have like nodes that we can return back in the model. And then we should be able to like loop over these things and like print their translations or something. Let's just start there. So can we go like for int I equals 0, I is less than model num nodes plus plus I, and can we like print f their translation? Wrong language. Nodes I translation 0. Okay. So we go like comma 1 2 like this, and then maybe their parent as well. All right. Why did he get lower down? I feel like there's maybe some like unapplied transforms. Or maybe we moved him down as part of something? I don't know. I don't know. But at the very least, everything has a parent of 0, which is concerning. Because this should be nodes U here. That's why. Okay, so that's good, right? We're seeing that like these guys seem to be parented relatively correctly, right? We probably have like, 9 I would assume is like his pelvis. No, maybe 11 is his pelvis. 11 might be the armature. But we're seeing like, a bunch of parented to 9. Then his like extremities are all parented to like the shoulder bones, probably. So it looks like, and these translations are like maybe sane. We can try rendering these translations and see what they look like. So can we like make like a bone? Or we can like render a bone, and we can kind of render it as like a line. I think that probably makes sense. So can we like, we don't have to get crazy with it, right? We can just be like GL you make bone, and we want our bone to just be rendered as like 0 0 0 to 1 1 1. So can we kind of use the same shader to render the bone? Which means that we probably just want like position buffer, and that's it, I think. And we just need to make sure that like this guy is like has the right data, right? So we're gonna have like 2 vertices, probably 3D, I guess. So we'll do like 0 0 0 and 0 1 0, and we'll be like size of verts here and verts, and that's probably fine. So if we like make a bone now, GLU bone vow is make bone, and can we just like render the bone here real quick? So can we do like draw me 2 things with the bone vow like this? That looks promising. We do see a very thin line there. We should crank up the GL line width. Can we like make it like 5 or something, just so it's like kind of more visible? Good. And then can we also make it brighter? Can we just like, we'll just do this for now. Let's make it bright as fuck. Cool. Okay, so we have like a bone, right? It's not really showing us much because we're only showing 1 at the center. But it would be nice to then start trying to render the positions of all of the nodes that we have. And we can do that by first of all, can we... There we go. Okay, so that's kind of more centered. And we can go for each bone or something, do something. So, not bones, nodes, sorry. Our nodes are not bones necessarily. In our case, most of them are bones, but they don't have to be. So can we go like for int I equals 0, I is less than model num nodes, I plus plus. Then we look at like model nodes at I. And we have like the translation. Let's just start there. Because we have this thing. So we have like this. Boom, boom. Boom, boom, boom. Kind of like this. Okay, so this is like the bone transform, right? And we probably want to apply this before the world transform, I think. So we probably want to do like bone transform, then world transform, and then set this as the world transform that we are rendering with. So we go boom, and then we draw the bone. So this should draw, that's something, right? We're seeing kind of like a bunch of like offsets of these guys. I'll be migrating to Andrews. Have a nice weekend. All right, see ya. Okay, so like we were saying before, these things are all in like local space, right? So if we want to kind of like, we're seeing like his leg bones relative to his like pelvis bone and stuff. Like they're kind of like off and to the side. But then like kind of going forward, we need to like apply rotation as well. So rotations in these guys are defined as like quaternions, where they kind of have like an axis angle representation, right? So you have like some arrow and you're rotating by some amount counterclockwise around that arrow. But they represent this in terms of like 4 numbers. So they have like X, Y, Z, which this is like the angle, plus like real, where they have like some like real component of this thing, where this is like kind of like a 4-dimensional imaginary number type shit. And then kind of like the sum of this is 1. So they kind of like multiply this unit vector by like sine theta, and this is like cos theta, where theta is like kind of, yeah, how much am I rotating around this thing? I think these are actually like over 2, because quaternions, they have a way to represent like the same rotation twice or something. And I think the reason that they represent it this way is that this kind of creates like a 4-dimensional sphere that you can like interpolate around, that creates like nice interpolations. So that's kind of what this guy's for. So what we want to do is we just want to like convert this into like a rotation matrix, because we're not going to be doing any interpolation right this second. So if we look up like a quaternion to rotation matrix, there's just like a formula for this that I don't really want to type out. But it's this. Right? So what we're going to do is we're going to write out like struct mat 4x4 mat 4x4 from quaternion, and we're going to take in like a float star rotation probably, or maybe quad. And I'm just going to like put this next to another rotation function that we have here. And I'm just going to be like implement mat 4x4 from quad, assuming quad is of the form x, y, z, w. He should be able to do this for me. He should. We can kind of trust him first, and then kind of see how fucking wrong he is later. if it looks kind of right, we don't have to worry about it. We do see promise that if we compare here, we do see like, this does not look the same, huh? We see like 1 minus here. I don't see a 1 minus anywhere in here. But maybe he's just using a different formula. Who knows? Who knows, dude? Let's just, we're saying xy minus zw. So that's this, at least. There's probably some like positive negative shit. But like, 1 minus. Yeah, that's interesting. I don't know why this looks different, but maybe there's like multiple formulas for it. Let's just not think about it. Let's just not think about it and we'll see. So can we rotate these guys as well? So we're gonna be like multiply. We want to do the rotation first, I think. So kind of can probably just feed it this. I mean, that looks somewhat promising, right? We have his the bottom half of his legs are upside down here because they're supposed to be like locally translated from their parent. So we need to kind of resolve the parent. We kind of have to like, we have to do our transform relative to our parent transform, right? So we can kind of like take all this stuff and just say like, mat 4x4 node global transform, or node world transform is probably a better name for this. And he's going to take in probably like a set of nodes as well as a node index. Okay. So he is going to node comes from nodes at index. And then all we have to do is before if we have a parent, we get his transform and do that after our transform, I think. So everywhere we say bone here, this should be a node. So we do node world transform from nodes and node parent, and we do that after we do our local transform. Yeah, fuck it. Then we return that. So then down here, we should be able to be like, struct mat 4x4 bone transform is node world transform from model nodes and I. Cool. And then we have to apply this before the world transform, or like we have like we're like rotating this guy as well, right? So this has to be done after. So it's like world transform here, I think. There we go. No, that's not looking quite right. I'm concerned about like whatever the fuck these are. These like upside down ones here. It could be because our quaternion function is wrong. That's like very possible. I would like to see. Oh, we have to apply. We forgot to do this. We have to assign the thing we did. That's better. I think it's hard to tell because I think we're not applying scale to this thing. So I think that if our guy's really small, that probably is about right. So we want to do rotation. Okay. So in order to get like the order of operations right, if we translate then rotate, that's bad. We want to rotate then translate, probably. Yes, because yeah, we rotate then translate, And then scale just has to come before translation. I don't think it matters what order. So can we do like mat 4x4 scale, which doesn't exist yet? So node scale 1, 2, 3. Then we do the rotation. Then we do the translation. Okay. Something like this. Cool. Let's mat 4x4 scale with an x, float y, float z. And this is going to look very similar to like the translation matrix, right? So like we were saying before, if you have like 1.0 on the diagonal, it means that like x gets applied to x, y gets applied to y, z gets applied to z, w gets applied to w, and everybody else gets ignored, right? And so if we want to scale this guy down, instead of like just taking the x value, we just take, you know, the scale value, right? So we kind of just decrease this or increase this by whatever the parameters are here. Okay, and then did we actually do this? Scale, rotation, parent. Okay. So I'm a little concerned here. It feels like the bones are just like way too big, is kind of how it feels. Make bone, right? So this guy is like going from 0 to 1, right? That's kind of like his thing. Can we overlay this on top of the guy? That might give us some information, right? So like, it does seem like the root of the bones are kind of in the right spots. It's possible that like the scale of the bones like are supposed to scale the vertices. And so if the guy's just like kind of small, like the bones, like the bone size might just not be represented here. You know what I mean? Because if we do try to like line up like what's happening on his knees, right? Like we have one bone here, and then like at where his knee comes in, you get like another line coming out. I think it's right. It's just it looks kind of fucking weird. I think if we just like increase the size of everything here, it might start making more sense. Right? If we just make him bigger and apply all transforms, I think, and then export this, it might start being a little bit more sane. We'll see. Hack, and then GCC. No, that did not fix it. Okay. Can we undo that then? Okay, let's for now just kind of reduce the size of the bone. And that will kind of just tie us over for now. Because I'm pretty sure it's right. What is this, like, shit falling off his ear, too? That's kind of surprising. That looks kind of like a bug. It could be, like, something else showing up in here that's not supposed to, so... I don't know, whatever. We'll think about it later. It's fine. Let's just look at the bones. Bones, 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 bones. Okay. So let's hide our guy. Oh, it's this. I just uncommented something that I wasn't supposed to. That's why. Okay. There we go. That looks kind of reasonable. Okay, so we have now, I guess, like, imported bones. And I guess the next thing is to do is to try to animate them, right? So let's look here and look for animations in the GLTF file. So the way that these animations work is they kind of have like many like channels. Each of these are kind of like representing like one movement of a bone over time, is kind of like what each of these things is. So this is saying like, hey, move node 4, move his rotation according to like the rules in sampler 13, right? So if we look at samplers, these guys have kind of like time steps here. So the input is like, what time stamps am I going to be doing these things at? And the output is like, what values am I going to use here? So let's think about like how we want to represent this stuff in like a way that we want to parse out from Sealand. Probably like we probably like make each channel, each like thing that moves could be its own file for now, I guess. And we'll probably set the type for this thing, right? If it's a rotation, it's going to have like different fields in it, probably. Yeah. Okay. And then we'll just like say we'll maybe put at the beginning of the file like how many time steps this thing is representing. That seems reasonable. And then yeah, sure. So we'll specify like his target, how many things, how many time steps there are, and then we'll put the time steps, then we'll put the like values. Sure. Okay. So here we should be able to go like for GLTF or for animation in GLTF animations, or maybe we just assert that there's one for now. Yep. So we'll go like assert len animations equal 1. Cool. Then we look at animations 0. And I don't know, man. We're gonna do like for channel in animation channels. We're going to say, where are we going? So I guess each of these guys gets like his own file, right? So we're gonna go like we're gonna be like open animation, open channel file, and then we're gonna write, you know, node number. We're gonna write type. Yep. And then we're gonna open the sampler. So let's just kind of start there. So I guess we'll do like an enumerate here. And then we'll go like with open like animations plus I with written as binary. We say f write channel target node. Yes. Can we do like, I guess this has to be like kind of like this. There we go. Okay. So we write out the target, and then we want to write out his type as well. So we're gonna go like animation type val, I guess. And it's like if s is translation, we return 0, I guess. If it's rotation, we return 1, and if it's scale, we return 2. Nice. Nice. So this is like a f right. These need to be like packed in some way, right? We need to do this like struct pack a like little endian unsigned integer here, and then I guess a little endian unsigned byte for the next one. Except we want to keep things aligned, so we'll just do online. We'll just do unsigned integer. That's fine. It was like animation type val. Nice. Okay. Okay. Cool. So that kind of handles that. Then we need to write out the number of elements. Right? So that's kind of the next thing. It's okay. So we have this like dump accessor function. This is like different though. So we are going to look at the sampler. Channel sampler. And then we look at our samplers, and this is like times is going to be like, I think that this is like a buffer view or an accessor, probably an accessor. So this is like dump accessor function. Can we write like dump accessor to file? That would be kind of hype. And then we can kind of just append it to something if it already exists. So it's just like instead of path, this gets output. Then everything that was like done in this function before goes in here. It just doesn't open the path. It already is already open. And then dump accessor with path is like dump accessor to file, GLTF accessor index output expected component type, expected type, boom. And then we just open the file before doing that. So we go boom with open path as output. We dump accessor to output. There we go. Yeah, cool. So now we should be able to be like dump accessor to file, and we have our file here, which is hype. And so we just have to like figure out the rest now. It's like we dump the inputs. I guess we need to know how many there are, which is probably something that we have access to. It's accessors count. We have that. Yes, hell yeah, hell yeah. Okay. So this is sampler index. Sampler is input. Okay, yeah. So times accessor is samplers, which is from somewhere. I think like this. So no, is it in the channel? Yeah, it is. Okay, samplers input. And we go like GLTF accessors, time accessor. What was the count? I think we write this out to the binary file as like this is how many time steps there are for this thing. Okay, then we just fucking dump that shit. Dump that shit. Okay. GLTF times accessor f expected component type. I don't know. I guess we'll just write 0 here and see how it falls over. I think it's probably floating point and scalar. Which 5126 was floating point. Okay. channel samplers doesn't exist. Great. What does? Oh, this is animation. Okay. Okay, that's promising. And then can we look at what came out of that thing? So we should have like, okay, first of all, this should be like .bin. Okay, cool. So we got a bunch of animations here. And in here, we should have, what is my target node? 0, I think is what, like, what is the target node? What is the type? So this is translation for node 9. There are 2 time steps, and here they are in floating point. Good. Now we just have to also dump out the output. So this is going to be like data accessor. And it should just be fine to be like, these things are vec3s, except this is going to crash because sometimes it'll be vec4s. Yeah, so here we need to be like, depending on the type of this thing, if this is a translation or scale, it should be vec3. Otherwise, it should be vec4. So, it's like expected type is vec4 if this, else vec3. And I think now it should kind of behave the way we want. Yes. Nice! Let's go, baby! Let's go! Okay, so now if we like look at animations 0, we should see this targets node 9. It's a translation. We have 2 time steps, right? So we're gonna have time step 1, time step 2, and each of these is gonna have 1, 2, 3 values, 1, 2, 3 values. That's really good. That's really good. Okay, so what's the next thing to do here? It's like, we need to load each of these animations somehow. So for now, can we just hard code like animation 0? Let's do that. So we're gonna look at like load file animations 0 bin with buff. Okay. So here we're gonna be like animation data. Is this. Cool. So we need to interpret this guy as like, it's the target. Yeah. Then it was the, the animation type. This is like the target node. This is the like target path. Then it was num times, time steps. And then can we just like print this stuff out? Target node, target path, num time steps. All right. So this is node 9, 0 translation, type translation, 2 time steps. Cool. That is promising for sure. Okay. So then we need to like parse out all of those things. So for int I equals 0, I is less than num time steps, plus I, we're going to do something. And it's like, I guess we're going to have like a cursor. And he's going to start at like 12, right? And here we're going to be like this. We move the cursor by 4 and we read out like, we have like num time steps times size of float is like where the times are going to go, right? And then we're going to be like times I is equal to a float representation of animation data plus cursor. And then we can go like for, int I equals 0, I is less than num time steps. Can we like print the times? Yeah, yep. So that's good. These are some time steps that are like, going up in number, starting at 0-ish. That's not crazy, right? Not crazy. Not crazy. Okay, so what's the next thing here? We need the positions. So depending on the type of this thing, we're going to like adjust this thing in some way. So I think what's going to happen is we're going to have like somewhere we have like an animation channel, right? This like thing that's like changing some bone over some period of time. And this thing might be a translation. It might be okay. Yeah. So we need a different type for like translation, I think, and rotation and scale because like the data is going to be different. Or we could just store this thing as like data and kind of figure it out as we go. Yeah, we could do that. So this could be like a enum animation type, right? Animation type is, we had translation equals 0, rotation is 1, and scale is 2. Cool. So we store the type in here, we store the data, and we still store the target. Cool. So as we were like ripping this stuff out, we need to store that stuff. So at the end of this, we're going to have a model that's going to have like animations, I guess. Yep. And each of these has a target, animation type, data, and not only this is not data. This is stupid. We need times. And data. That looks pretty good. Okay. So here we're like, I have my times. These are malloc, and these are going to go into some animation. So for now, let's say that we have like animations. We are going to have one of them because we don't know how many we're going to have yet. So okay, now we're going over like our first animation here. We're loading him in. And this is like for int animation index is equal to 0, animation index is less than 1 because we don't know how to deal with this yet. Yeah, we load each one. Boom. This is going to have some sort of like, path management shit going on. But that's fine. Target node, target path, num time steps cursor. We get the times. we malloc the times, and then we have the data. So num time steps times 4, like this. Or we could do this as, we could like try to like compress the data a little bit if it's translations, but whatever, we'll use 4. So we do this again, right, where we're going over num time steps, we're reading the cursor data, we're getting floats, except that I guess we do need to parse the type. So we'll do like components is 3, and then if the like target path is equal to oh, this should be like animation type. We need to prefix these. I forgot. In this language, these things are global. Animation type rotation. Components is 4. Because there are 4 if there are rotations, 3 otherwise. Now we can do this times components. And we get like data I times components is this 3 times. I guess 4j to num components. We do this. Yeah. No. Start is data plus I times components like this. Then we use start and j here. Yes. That looks good. Okay, hype. So now we should be able to say like animations at animation index are equal to something. So like what? It's like an animation channel with this stuff in it. Yeah. Okay. So it's target node, target path times data, and then clearly we need like num time steps as well. Surely, right? Surely. All right. So does this run? It does, and we should be able to like do something with that information. Like maybe just print out the first animation. Okay, where are we at? Where are we at? We want to like load the model, and after we load the model, let's say like animation channels 0 num time steps. We're going to say that like at this time step, we have this data. We have at this time step, we have, you know, we're of this type with these first 3 components. Yeah, sure. So this is times I. We have, I guess like this data. And this is like I times like 3, I guess. Because we know this is a translation. Segmentation fault? That's not good. That's not good at all. What's going on there? We don't have GDB. It's annoying. That's annoying. Get me some GDB, please, sir. Sir, I'd love some GDB. Okay. Where is he pissed? No debug info? True. Okay. Oh, that's helpful. That's really cool. So I can't even look, but we can assume. Oh yeah, I don't know what the fuck I'm thinking. Oh no, wait, that does seem fine. Unless we didn't assign animation channels, which we probably didn't, to be honest. We probably just forgot. We probably just forgot, and this language doesn't stop us. Okay, cool. So we do see that this guy sets some values at some times, and they're basically the same. So this, whatever bone this is, just does nothing. Right? And that's just like in the animation data for some fucking reason. But that's fine. Okay, can we kind of look over every single animation now? I think that we probably can. So first of all, this guy needs to store how many animations he has. So we're gonna do size t num animations. Uh, for now, I just want to hard code that shit so we can see 29 in here, and I'm just gonna hard code it because I don't want to deal with it right now. Interesting concept for a stream. Do you mean you're learning Hello World 3 anime character, or do you mean teaching? I mean, teaching is strong. I don't know if I would say I'm a teacher. I would just say that, like, we did this over some period of time, like over a couple weeks, kind of like interspersed with other stuff. And I think that it's cool to get it all at once because I think that it's like, I said at the beginning, like, I think it's just kind of like beautiful the idea that, like, not that much stuff, like conceptual overhead, there, like, doesn't you to render a 3D character with animation is actually not that hard. Like all of the concepts are quite simple. But you have programmed before. Yes, I have programmed before. Um I'm kind of viewing this like I studied for the exam and it's exam day, you know? Like that's kind of how I'm viewing this. Okay. So animations. So let's just rip over, what do we say, 29 of them? So let's just hard code a fucking 29 in here, and then we will kind of construct this path somehow. So can we go like a, path buff with like, we'll give it, a bunch of space. And can we like print out animations percent %d dot bin like this with animation index pipe? Then does this tell us how many characters it was? Yes. Int path len, and then we just go like, I guess we don't need the path length though because it's null terminated in this language. So that succeeds. And then I guess we probably have to write down how many of these things there are. So we're just going to write down like a 29 here. And then wherever the fuck we were printing this stuff, we're going to go like for animations. I is less than model, or animation index is less than the animations, number of animations plus animation index. All of this goes like in a loop. And now we should see them all printed, I think. We'll see. Let's maybe printf like animation this, right? Okay, so this is promising, I think. This is not promising. That looks fucking sketchy as fuck. Yeah, so there's some like invalid data here, it looks like. Oh. This looks wrong. Animation channels, animation index. Oops. Okay. Does that make more sense? I think this is wrong. What am I looking at here? I times 3. So the times 3 depends on how many components there are. So can we like can we look at like do something that's like int animation channel components from animation like animation type, and we should just be able to like switch on animation type, and if we have like animation type translation, it's like return 3. I guess also for scale, it's 3 components. Does animation index just take the current length of the list and add 1 to assign the index? I don't know. I'm not really sure what you're asking. So this is 4 components for rotation because they're quaternions. So now this should be like int animation, like number of components here. Animation channel components with the, you know, the index of this guy and the type. This is like components. My Rainer, thanks for the raid. What's up, you guys? We are in the middle of kind of like, how do I say this? Okay, so it's worth giving a little bit of context. So we're kind of working on like this game, right? And this is our game so far. We have our little guy that we modeled in Blender. He's got a little wooden sword and shield, and he's running like a fucking idiot, right? We're not going to go into like the specifics of the game for now, right? But this is kind of like a thing. We've been working on this for a little bit, and we kind of went through like the whole process over the past few weeks of like designing a guy, animating him, rigging him, like setting him up in like an OpenGL environment with like no game engine, right? And so to do that, we had to like learn a bunch of concepts, like how does bone movement from Blender deform a mesh and stuff like that, right? And we got to the end of it, and I was just kind of like excited by the idea that like we got to this from essentially nothing, and no piece of the like no individual component was like that difficult, right? But like the sum of all these components makes something that's like kind of complex. You have like lighting, you have shadows, you have like smoothness on the sky, you have like texture mapping, and all like you have like like smooth skin deformation according to the bones, right? So like I was just kind of like, it's cool that that can exist, and it's cool that like anybody could kind of have that knowledge. And so I kind of wanted to just do like a like write the exam type shit, right? Where we're like, let's try to like go from like 0 to the full thing in one sitting, just to like prove to ourselves that like 1, it's not that complex, and 2, like have like all the information collected in one spot, and 3, just because it's like kind of a fun little challenge. The YouTube videos and Twitch streams love timed challenges, dude. We love that shit. So that's what we're working on. We kind of got to the point where we did this again today. We're kind of at a point here where we have like bones loaded for a guy. We have the mesh loaded for the guy with some lighting, and now we're trying to like basically like animate the bones according to these parameters. So we're just gonna keep moving. Thanks for the raid. Hope you guys had a good time over there, and we're gonna keep moving. You should sell plushie merch, dude. A plushie would be so sick. I like just having one for myself would be fucking sick. Okay, so I think here, I guess here we should go like, we should print the time directly. I guess we can just do like, it's fine. We're missing the like W component of rotation on the rotation targets, but it doesn't really matter. I think that we're looking at this. It seems pretty reasonable that like this animation for like this guy waving has like what seems to be a contiguous set of times and a contiguous set of values for these things, right? So I think we're in a pretty good spot. You should try animating in UE5 sometime. The tools have gotten really good since 5.4. I doubt I will ever do that. Like, I'll just be honest. Game engines aren't really my cup of tea. I'll be honest. I like I like getting in the dirt, you know? Okay, so we have now what seems to be a list of animations that is pretty reasonable, right? And all we should have to do to apply these animations to the bones is like a, set the values on the targets, right? So we have like we probably want some sort of like animation runner or something, or maybe we can just get away with like a bop, 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 bop. Let's think for a second. Can we have like animations? We should just be able to get away with like a function here that's like apply animation, right? And we're gonna take in like a time since start probably, as well as like the animation list probably. So maybe we just take in the model. And here we have like model num animation. So we're gonna do something for each of these. So I guess like this print loop is gonna look very similar to what's actually gonna be done, right? Model here is a pointer, I guess. So anywhere we have model dot here needs to be replaced with model arrow. I guess it probably makes more sense to do like find to this model arrow. Boom, 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 boom. Big waves from the writers. Hello, hello. Okay, so let's just call this like on every frame we're going to apply the animation, and I guess we can just do this once off rip, and then we can kind of like cover the rest later. So we're gonna say time since start 0 with model, and let's just see if like we can get like a sane initial pose from this guy. So right now this should like just not crash and print something interesting. He does crash, which is not hype. We don't like crashing. In compile shader, that's kind of surprising. Corrupted doubly linked list. That's quite surprising. That's like we're like doing like use after free or something. That's quite surprising. Maybe this. Maybe we're going out of the bounds of buffer. I didn't think that should happen, but I guess that's kind of possible. Okay, let's say we just did like 1. Oh, that would segfault for a different reason. Hold on. Can we... Oh! That would do it. Maybe we should write like a number here. Size t num animations is 29, and everywhere we have... so we usually use that here. Dude, silly C. Silly C, it's so easy to memory corruption. I mean, of course, we should be mad at ourselves for hard coding memory related constants a bunch of times, but we don't have we can be mad at someone else. Okay, so let's try to apply the animation now. So for each channel, for each time step, I guess we are going to try to find which time step we are at. I'm concerned that I'm seeing like non-zero time steps for like the base of this thing. I'm kind of curious to see if maybe we should kind of select everything and just kind of move it back by 1 frame. Because I think if we export this GLTF, hopefully the values are like a little bit, they're like 0 instead of 0.04. Because otherwise I don't think that we're going to behave the way I want. Okay, that's better. Okay, much better, much better, much better. Okay. So now what we want to do is we want to find the first time step that we are greater than, I think. So we probably want to do like rel time or time since start. We want to like make sure that we're within the bounds of the animation for the channel. So I guess it's like for this channel, rel time since start, we're gonna do like time since start over, I guess, like the last time step. So can we do like, let's try to like alias this a little bit. So struct animation channel is this, which means that we can kind of do like channel num time steps -1 indexed into times. Okay, so this will make us like make sure that we're in the bounds of the animation. Mr. Bossman, sir, any specific reason you're using NixOS? Thinking of switching it to try it out. Okay, so this is one of those things where like I wouldn't necessarily recommend it to people, but if you have found it on your own and are considering it, it's probably interesting to you. I like it because I share like a configuration between all of my computers. It was really easy to try in a virtual machine because you can just like set up your config and then copy paste it to the real machine after. Um, but I like it because I like track a bunch of stuff in like a Git repo. Like I was reading through my like Git history in the other day, and like I have some like patch to like the steam.desktop file that turns off like its attempt to prioritize using the secondary GPU. And I have like notes in there being like, oh yeah, I did this because I was playing PlateUp. PlateUp was always rendering on my integrated GPU instead of my discrete. And so I need to like, if I change this environment variable in this file, then like that doesn't happen anymore. And it's just like, it's sick that like I have that patch stays forever. And I never like, it's in my history with exactly why it happened. Like that's just awesome. Right? Like, but you're trading off like, there's all sorts of reasons that using Nix sucks, and you're trading off those reasons for having something like that. So that's why I use it. Okay. Focus. We're so deep in the fucking stream right now. We gotta lock the fuck in, dude. Rel time since start. So we just need to find which time step we're at. So we iterate over these guys. We're like, which one are we? So if, I guess it's like, if our rel time since start is greater than or equal to channel num time steps at I, we break. Okay, so now at this point we know like I is the appropriate time step. So can we say like last time step, I guess, is a better name for this? Okay. Then we have like next time step is last time step +1, and we should just be able to like linearly interpolate from like our parameters to the next parameters and how we, and then like apply them somewhere. So I think we want to go like float out. Probably we'll just make this 4 for now because like rotation and translation, they might be different, but whatever. We get like the animation channel components from the channel type. Yep. Int components is this. We go like for int I equals 0, I is less than components. Sorry, yes. And we like set this output parameter as like a lerp between the two. So we have like, you know, the channel data at like last time step times components. Yes. So this is like float star last data, I think. I think that works. And then next data is next time step times components hype. So now we should just be able to go like out I is equal to lerp last data, next data, and we probably need to like lerp this shit according to a time step, which is what? It's like how far between the two we're at. So this is like you know, last time is like channel times at last time step, yes, next time is this. And then it's like the lerp value is time since start minus last time over the distance between the two. Yes. Yes, 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 yes. That looks pretty good. So now we just need to do like lerpy lerpy. Float lerp. So we have A, we have B, we have T, and it's like A times. So if we're like at 1.0, we're at like maximum B. So it's like A times 1 minus T plus B times T. That sounds right. Fuck it. So this is I here and I here. Woo! That sounds pretty nice, dude. Okay, so now we have this like out components thing, and we need to like apply out to somewhere, right? So we'd have this like animation thing. We have like channel target hype. So we're gonna like take the model and we're gonna look at nodes at the target node. Yeah. And we are going to adjust this guy's like parameters according to this. So we're probably gonna like switch on the channel animation type. Oh, we're so close, dude. Oh, this is actually so fucking close. Okay, so if we're translation, we go like node translation 0 equals out 0. Oh, yeah. 1, 2, 1, 2, buckle my shoe. Shut the fuck up. What are we fucking talking about? Rotation. So this is like rotation here, 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 and this guy's got 3 parameters. We probably could just mem copy, to be honest, but like whatever. Okay, and then scale, delete the last one. Oh, that looks pretty fucking good, dude. That's a fucking initial pose, dude. Dude, look at dude, look at the thing. Okay, hold on. Let's bring him a little closer. Look at that. He's fucking paint me like one of your French girls. Okay, we're actually so fucking close then. I think it's just every frame we do like now minus start. Yeah. Uh, Close. I think he's we're maybe fucking up the looping just a little bit. Maybe. But like the first like quarter of a second there looked kind of good, dude. uh Now that's what it looked like in Blender. Yeah. Let's just double check. No. No, it wasn't. Okay. So what's happening here? Can we print out the rel? Are we doing something stupid like using time since start? We are. We should be using rel time since start. Close. Why isn't he lerping himself back? I think that maybe like every single bone for us, we need to duplicate his start and end for it to kind of have like the correct end time in the animation, would be my guess. Probably there's some way that you're supposed to like set like read the bounds that we're not doing it right. But I think we can hack it like this. No. That's interesting. So we are fmodding this to the last time. Do we have like time steps written in here still? I would love to like print this stuff. We're so close. It's just like Okay, so like how long is this supposed to be? This is 24 FPS at 10 frames, so we have like 10 over 24.41 ish is like the animation time. Okay. Which is about what we were seeing in there. So it looks like he's kind of going womp. He's making it there. And then immediately snapping fucking back. Which is just strange to me. Like, let's just, like, if we were to cheat for a second. No, that's not doing it. I'm worried that, like, num time steps. Oh. Oops. We've got, this is wrong. So we're always interpolating between the first and second thing, like dumbasses. Because this is going like 0. Am I bigger? Yes. Sick. Right? And I'm always bigger than 0. So we should be iterating this backwards. Right? This would be like channel num time steps greater than 0. Then we immediately decrement this by 1. I guess we can do greater than or equal to and -1 here. And then that should be a little bit more sane. There we go. Let's go, baby. We got some fucking animated bones. That is fucking sick, dude. Look at that. Okay, so the last stage here is we have to apply this movement to like the mesh, right? Because don't forget we have a mesh here of our guy, right? And we just need to like deform the mesh according to the bones. So how do we do that? How do we do that? So in the GLTF file, there are kind of like parameters that say for each vertex in my mesh, who affects me? Who affects me? S coloring lighting. No normal coloring. Oh yeah, we can turn that back on. It was just because it was easier to see the bones that way. Right, we kind of just did like that, you know. It's just the bones are like dark now, right, which kind of blows. But like sure. Right, okay. So these bones have positions on this guy, right? We go to layout, we look at this like this guy, or we look at the animation, the armature, right? They have like default positions. And when they are like rotating, they're like rotating in local space. But like our mesh kind of has like vertices kind of just all over the place, right? So like for this vertex to be edited by, you know, this mesh or this bone, we kind of have to say like relative to that bone's initial position, where am I? Right? Which is like a thing that we have access to. There's kind of like a transformation that takes the bone from like its default position to like default like 0, 0, no rotation. And then we can like apply that to our vertex, then apply the bone transformation again after. And that should put our vertex in the right spot. I think probably the first step here though is to try to like figure out which bone each vertex is related to, because that's the most important initial step here. So if we look at the asset untitled GLTF, here somewhere they have like skins, and the skin here says which joints am I associated with. I don't think that's what I want. So this is like a list of joints, which is important, but I don't think is like the most important thing here. This is what I'm looking for. So the mesh has at each joint, or for each vertex, he has a list of, I think if I remember correctly from last time we looked at this, it was a list of 4 joints. So he might say, like, given this joints array, 90210 Beverly Hills. Given like this list, I might say that like this vertex looks at, joint 0, 2, and 4, and I am like, 50% modified by 0, 25% modified by 2, 25% modified by 4. That's kind of like what this thing has in him, if I remember correctly. So let's first start by like loading this joints data. Can we look at like accessors? So we have like accessors 0, 1, 2, 3. So vec4, yeah. Yeah, okay, I think that's right. So if we go into our like little extractor guy, we should just be able to be like wherever the fuck we wrote like position and normal. We should just be able to write like joints 0, and we'll call this like vert joints. And we're expecting vec4s here, and I think we're probably expecting like a scalar, like a integer type here. Weights 0, we're expecting a floating point type. So I think this will crash. Vert weights. I think. Oops, pack GLTF. Yeah, so he's mad because I think this is probably like unsigned like short, or we'll just change this number until it fits. Okay, or we could read with our brains and our eyeballs. Fine. If you want, if we're fucking supposed to use our heads, we'll use our heads. So joints 0 is accessor 3, so 0, 1, 2, 3, 5, 1, 2, 1 is what he's expecting. Cool. Cool. So what the fuck is 5, 1, 2, 1? That's like an important piece of information. Unsigned byte, I see. So these guys are 1 byte joint IDs. Okay. So we should be able to like load vert joints buff here, which was vertex joints is what we called it. I already forgot. Vert joints. So we have the vert joints buff and the vert weights buff. Okay, and what we want to do is we want to get these things like onto the fucking GPU. Right? So can we maybe do something like let's make a joints buffer, which, takes the stuff that we got in and he puts the into index 2 in the vertex shader. This thing is going to be 4 things of GL unsigned byte, is what we saw. And we have to be very careful here. This is attrib I pointer for integer, not attrib pointer, and these things are going to be, apart from each other by 4. They're going to be spaced 4 apart. Okay. I think that's fine. So now we should be able to go into our like vertex shader and add in a layout 2 that is a u vec4 of v joints. Okay. And if we want to kind of highlight which joint is most important to us, maybe, or like which parts of the mesh are seen by which joint, we can maybe do something like in the fragment shader. Go like we have some uniform like preview joint or something. And we can say like maybe it makes sense to go here. And we can say like we'll have like an input here that's like joint, like joint coloring or something. I don't know. Doesn't really matter right now. So here we need like an out float joint color, and we can say like if we can say like joint color is equal to 0, right? But if the v joints 0 is equal to preview joint, yeah, then joint color is equal to 1.0. That kind of seems right to me. Then we just have to like visualize that thing in some way. So can we just visualize this as a joint color? That seems kind of nice. So can we kind of predefine this thing as 0? Can we also stop? It's likely that we're like compile erroring and just not noticing. Can we like get rid of these like printfs of the normals? That's like fucking annoying. So that's not happening. That's kind of surprising. I don't know where we went wrong here. Index 2, index 2, size 4, type byte, stride 4, pointer 0. That seems kind of right. Color is commented out in the shader. Yeah, that's true. That's a pretty good point. Okay, too few components construct vec 4. True. So can we just do like vec 3 joint color and 1.0? It's a pretty good point. Okay, so those are the things that are affected by joint 0. Joint 0 is kind of fucked up because there are some, they use joint 0 to also represent null. So it's like if v joint 0 is going to be v joint and v weights. No, this is, we're only looking at v joint 0, so that should be okay actually. So can we like change this to look at like v preview joint 1, right? And we can see that like that's only affecting his head, right? And 2 is only affecting his left arm. So I think that's like a really, really good sign that like the joint parsing is working correctly, right? And we could even like, you know, we could show like less of him. There we go. There we go. Okay, so now can we kind of like color these things according to their weights? So let's parse the weight data as well as the joint data here. So in the same way that we did with like joints buffer shit, we're gonna basically replace everything that says joints here with weights. Like we do like weights like this, like this, like this, like oopsies. Boom, boom, okay. And then this is now going to be index 3 is going to be where we're going to look at the weight stuff. And weights are going to be a vec 4. Okay, and we have to be careful because we did integer last time. This is now back to being floating point. So GL float, and these are not normalized, or we don't want you to normalize something. I don't know, just like don't fucking touch my data, please, sir. And now can we kind of like do something that where we go like for int I equals 0, I is less than 4. We look at all of the possible joint values, right? And in here, we say like if v joints I is equal to preview joint, then and v weights I is greater than 0, then joint color is now equal to v weights. Okay, so we're getting a little bit more advanced. A little more advanced. So now we should be able to see like, you know, kind of some highlighting here. Can we maybe get rid of the... Can we stop drawing the bones for a second? Close. It looks kind of fucked up though, right? I think we probably want to break. We might have forgot to do like a... Although that shouldn't make a difference. Yeah, I'm a little concerned there. I'm a little concerned. That doesn't look right to me. Like, we're kind of like in the right area, but the weighting is like definitely fucked up. So can we just like double check this again? For int I equals 0, I is less than 4. If, oh, maybe this should be like this. No. So if joints I is equal to the preview joint. Cool. And the weights there are greater than 0. So it feels to me like we're uploading the weights wrong. So we load vert weights.bin. Did we get the location of this guy right? Did we fuck that up? V weights location 3. Okay. Vert weights buff. We get a weights buffer. We load that shit. Oh, this is wrong. Oops. Classic fucking byte offsets. There we go, baby. That's looking pretty good. Did I want the break inside the if body? Yeah, probably. I'm a dumbass, but it also doesn't matter. There we go. Okay, so let's try like joint 0. Yeah, that's looking pretty good. That's looking pretty good. So we're now seeing kind of like, you can see how it like kind of fades away now. So like it will kind of affect some areas more strongly than others. That's pretty hype. Okay, we're really close. We're actually so close to getting like the whole shebang done. I think the last piece here is, like we said before, you know, he's got like his T-pose and he's got like skin kind of related to some bone. We need to go like to the center of the world, then back, right? So we need like inverse matrices here. Inverse bone matrix is, we're gonna have like 20 of them or something. And we also need like the forward bone matrix. Like, so we're gonna go backwards and forwards. Right? So here we have to do something that's like our position. We have to do something that's like related to like the weight as well, right? So we I think it's like GL position. We need to like kind of nuke this guy up front to be empty. I think. Then we kind of like add on the weighted transform here. So it's like GL position plus equals, we take the R position and we multiply it by like all of this stuff. All this stuff we were doing before, we keep doing this, but we just kind of throw in like a double transform here. So we go like inverse bone matrix at like V joints I, and then a forward bone matrix at V joints I. I think it's something like this, right? And so can we temporarily just set all of these guys to identity matrix? And if we did that correctly, then everything should kind of even out, I think. We have GL position equals here. This should be plus equals. And we forgot to times all of this by the weight. Yeah. I don't know how brackets work here, so I'm just gonna do it like this. I think that's kind of right. So can we do something that's like inverse mat struct mat 4x4 inverse bone matrices 20, and then can we like mem set this to identity for int I equals 0, I is less than 20, I plus plus. We do like inverse bone matrices I is equal to mat 4x4. If we do translate of 0, that's the same as identity. And then we also want like bone matrices to do the same shit. and then we need to like set these guys. So we want to do like 3. We have 20 of these guys, and we're looking at like inverse bone matrices here. And can we like do like a void star here? Okay, and bone matrices. Okay, so that's not good. It's syntax error at line 9 in the vertex shader probably. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we do need types here, huh? That's not good. So no syntax errors, but it's definitely not doing what I wanted. Okay, so let's go back for a second. And let's kind of just do this at like index 0 here. Yeah, something like this. Okay, so even that's not working. Let's take this out. Okay, so we like fucked this shit up good, dude. We really done fucked it. I don't really know how. It feels like nothing should have changed here. But it has. Yeah, so we somehow done fucked this shit good. So we're taking vpause, world transform, viewport transform. I mean, it feels like the same shit, dude. I mean, pretty clear. Oh, God. I wish we had checkpointed. I guess we just have to hold undo until it works good again. And just try to be careful not to actually edit anything. So here, was it working? No. Back farther. Here, for sure, it was working. Okay. So can we just copy paste the vertex shader at this point and then go all the way back to the end? And comment this out just to see. Okay, so we're back to working. Okay, so it's something that we did to this vertex shader is wrong. So we have this for reference. In fact, let's just do a little git add dash u, git commit dash m smile. Let's just, just so we have somewhere to go back to. Okay. Oh, maybe the joint color was always 0. No, I don't think so. Okay. So this is broken again? Yes. Okay. So what is different here? GL position. Basically the same. Just no brackets, so that's not it. Oh, fuck. Oh, I didn't mean to close that. Okay. Where am I? Wrong one. Okay, there we go. So, am I high? Right, where you just set the position to the world transform and the viewport transform? Like, hello? And it is related to this. Vpause 1.0. Am I stupid? Can we like copy paste the contents of main here? Like, I feel like nothing's changed. Confusing. Confusing. I wonder if these location things don't work correctly. Like, if I just comment this shit out, that's weird. So maybe we have to be a little bit more careful with this stuff. I don't really understand. Maybe it's like failing to link and we don't notice. Can we just be like, we might have to do something like that. Aha. So location here probably just needs enough room for this stuff. One location per array element. Yeah, I think that's correct as well. Okay. So can we go back to trying to apply this with a like inverse bone matrix or something? So it was like, you know, we're gonna do like inverse bone matrix b joints I times bone matrix b joints I, right? That was kind of like the thing we were gonna do, and we're gonna multiply this all by vu weights I. Right, we're kind of going to do all this. Unlucky. Unlucky. Okay, so let's go back to commenting this out and maybe try using the bone matrix 0. Just kind of hard code that. Unlucky. So that means that probably the inverse bone matrix and bone matrix upload are wrong because we didn't use the right locations. This is 20 and 40 now. Right? That's kind of what we said. Still no bueno. Okay, let's just try to do one of them. Only bone matrix 0. No, nothing. Interesting. That's quite surprising. Do we have to set them all or something? I'm not really sure. I'm not sure why this is not doing what I wanted. Very surprising. Can we do something like this? It's bone matrix. Let's see what happens if we do that. Still no. Interesting. Is the program failing to link? No, because if we take out the bone matrix stuff, it's back to working, right? No. Whoa. Whoa, 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 whoa. Oh, I have a plus equals in here, which is pretty fucking stupid. That's better. Okay, bring this shit back. We're still good. Hell yeah. We multiply by bone matrix now. Uh-huh. Cool. Times inverse bone matrix 0. Still good? Hype. Okay, so now we go back to that hard code 20 and 40. Should be fine. Hype. Okay, and then let's go back to now trying to do this as part of this. So now we're going... There we go. Okay, we're back. We're back. So now we just have to set these guys correctly. So can we start with just the bone matrix? Because we have all the data we need to do the bone matrices now. It's kind of fucked up and stupid. Oh, we don't. We're missing in here, we need the mapping of joints to nodes here, right? So we have like this stuff. These indexes need to come out, and we also need these. So we can probably just like rip this all at once, I guess. So in our like Python preprocessor, we should be able to just like at the end of main here, go like GLTF skins. Here we look at like skin 0 and we look at like joints. We probably just like, you know, do something like this and we just like write this out to a file. So we'll call this like a joint info bin or something. We just do like a write this thing as a uint32. Fuck it. right? Something like this does not seem insane to me. Then we probably want to copy all of the inverse bind matrices. So can we, like, before we do any of this, write down how many of there are? So this should be like len joints. Right? Okay, so we write out how many there are. We write out the joint IDs, and then we just do like dump accessor to float GLTF, and then we look at like skins 0 inverse bind matrices, and we need like all the rest of the shit. So we dump out this. We write the expected type, so it's probably floating point, and mat4 would be my guess for the name here. We could check. Accessors 6. 0, 1, 2, 3, 4, 5, 6. Yeah, mat4. Nice. Okay. We should run heck. Okay, so if we like hex dump this thing, we should see joint info. We should see 10 joints, hype. So then we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 joints, and then we start dumping out their matrix values. Cool. Cool. So we should be able to now, when we're loading our model, we should be able to like populate the inverse bind matrices and the joint IDs. So let's go like joint info buff, I guess. I guess the model now probably wants to hold like num joints here, and probably like joint info. Maybe just like a node like joint IDs or something, and then maybe also like a mat 4x4 inverse mats. Seems reasonable. Seems reasonable to me. Joint inverse mats, maybe. Okay. Now we just start parsing the shit, dude. So, num joints is a uint32 star dereference of joint info buff data. Boom. Okay. Then we malloc, num joints times size of uint32. Joint IDs. Okay. We also allocate the inverse matrices. All right. We rip over. We like do the same thing where we have like a cursor, which here. Okay. So we start at offset 4. For int I equals 0, I is less than num joints plus I. We increment the cursor by 4, and we say that the joint IDs at I is equal to a uint32t pointer cast of joint info buff data plus I dereference that whole shenanigans like this or something. Gross, but whatever. And then we do it again, but with mat 4x4. This goes to inverse bind matrices, and this gets incremented plus 4 times 16 because there's 16 floats per thing. And then also we know that they store column major, we store row major, right? So we should add a function to do like mat 4x4 transpose to convert. It's a little silly to convert there and back again, a story by Bilbo Baggins, but whatever. So we return the breadth value, like for int I equals 0, I is less than 16. We go row is I over 4, call is I percent 4, and then we say like ret at call times 4 plus row is equal to in at row times 4 plus call. So that should kind of like flip it over the diagonal, which is what we want to kind of split from row major to column major. And then here we should be able to be like inverse bind matrices I is equal to inverse bind matrices I transposed. Hell yeah, dude. All right, that's like a maybe. And then we need to like assign this stuff. So our model now, it's, what's the order here? It's joint IDs, joint inverse matrices, and then num joints. Boom. Cool. Cool. So now all we have to do is when we like upload these joints to the GPU, we should just be able to like yoink them from the model. I think. So we go over each joint from the model. Inverse bind matrices I is like model. We actually can probably just like upload inverse bind matrices from the model directly. To be honest, joint inverse mats. This should just be able to like go in straight like that. And then bone matrix, we have to like we have to do like the world, like node world transform, yes, of model nodes at model joint IDs I? Surely, right? Surely. We might want to copy them here because this thing is expecting 20. Or maybe we do model num joints here. Yeah. Yeah. Nothing. Okay, that would have been too easy. It would have been too easy. So how do we want to do this? Can we go back to identity everywhere? Let's just, okay, so there's our little guy. There's a little guy. He's there. Recently, one joy I have is showing people who are way too much into clean code how matrix math is implemented in real libraries. Yeah, dude, it's kind of fucked. This actually isn't so bad. I know that like if you look into like BLAS libraries, like cuBLAS or whatever, like it starts getting like fucking crazy. Yeah, like this is actually not that bad at all. That's like about like what I would expect, to be honest. Okay. Let's maybe start by just applying the bone transform with no inverse, right? Maybe that will help us in some way. Like we can kind of see, we can like bisect how fucked we are. You know? So can we go like model nodes like this? Okay, so here you can tell that there's something very close to correct happening, right? You can kind of see how his skin is deforming. His arms are deforming with the wave, but it's like they're just like totally fucked. So it's likely more likely that the inverse is not working correctly. So let's bring the bone matrix back to identity and see if we can like gain some like intuition about the inverse bind matrices. So can we go like model joint inverse mats at I? Does that work? Interesting. That's like a, it's not that fucked up. Okay. Okay, so joint inverse mats. Do we not set it? Inverse bind matrices. We get a bunch of mat 4x4s. Okay, maybe we should print out the inverse matrices. And poor guy, what did you do? Yeah, we like ran him over, dude. So we're fairly confident that it's the inverse matrices. So it'd be interesting to try to print these guys. Can we go like row? If I%4 equals 0, we do like printf a new line. Otherwise, we printf a floating point of the thing. This doesn't really matter. With inverse bind matrices I. Right, let's just like see if this is... Oh, this needs to be J. This needs to be J. Okay. Yeah, like this. Like, how fucked are these things? Segmentation fault core dumped because this needs to be plus plus J, classic, we're incrementing the wrong index. Okay. So this is like... This is strange. Okay, let's we need to put like a... Hi, Mom. Yeah, this is not right. This is definitely not right. So let's take out the transpose in there. Let's see if like I'm fucking that up somehow. No, these don't look correct. There should be like a 1.0 in the bottom right like every fucking time. Right? So we're doing something stupid here. We are not using the cursor here, which surely we should be, right? Surely here we should also be using the cursor? Yeah, I think that we want to do like plus cursor in here. Don't use I for like the conversion. I think this is kind of more correct. No, that's really fucking broken. Interesting. Interesting, interesting, interesting. So, can we print the joints? Let's see if this is correct. 90, yeah, these are right. 90210, because we're 90214, because I was saying 90210 before. So that seems okay. It's these inverse matrices that just look like really fucked. They're like totally zeroed out. Okay. So it looks like probably this is not valid. Can we do like something else? Can we do like a mem copy into inverse bind matrices I from joint info buff data plus cursor for 4 times 16 bytes instead of doing this like weird wacky assignment? Does that kind of change this at all? That looks a lot better. 1.0 in the bottom right every time, and then we probably just need to apply the transpose as well. Let's fucking go, baby! Let's go! That's some pretty solid work for the day, dude. Look at that. Look at that. Okay. Yeah. All right, so what do we do? We had like skin deformation and like inverse bone transforms, like joint mapping and like weight joint weights or something. It's kind of like that. But I mean, pretty exciting stuff. So what's that? That was 4.5 hours, which is pretty long, right? This is like we're past like 30-minute shit, right? Get pushed. Yeah, I'll push this somewhere. We could do this now actually. But like in terms of like what we actually had to do in order to get here is not crazy, right? That's really what I wanted to like kind of show with this, and I think we succeeded, is that like this feels unachievable almost, right? When you're first getting into something, it's like this seems so fucking complex, right? But we kind of like walked through every concept we needed, and not just unlock the concepts, but we unlocked the concepts and implemented them in 4.5 hours, right? So like it's not crazy. I know we're moving fast, and like some of these things, like the first time I was looking at these like 4x4 transformation matrices, it took me like a really, really long time just to like understand what they are. So I kind of get that, right? It's like it's not like quite fair to say you only need 4 hours of like info, but like I like stand by that it is so fucking sick that you can get to something like this with like it's all the math is all simple. The hardest thing in all of this is probably the idea of like projection matrices, right? That one was kind of like the trickiest because you have to do like you had to do like that like solve for A and B from doing like after applying Z and the W, like you divide by Z, which means Z goes in the W, which means you have to solve for A and B to get like the near and far clip planes. That's probably like the hardest thing of all of it. Like the lighting, it's so fucking cool that like a couple dot products is like all you need to get this level of lighting. And it's like, of course, this level of lighting is not very good, but it's a lot better than no lighting, right? And like, I don't know. I just think it's so sick. And so I'm happy that we got to the end. Thanks for watching, guys. If you like what we saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 5:15 now, so kind of a long stream today. But it's because we wanted to get through it. If you want to keep up with VODs, we are working right now on our little game. This is kind of what inspired this, right? We're working on a game related to this guy. He's going to be part of some like RTS. If you want to keep up with that thing, VODs will go up on YouTube. We kind of split the stream into 2 segments. One we call Happy Hour, which is just like stuff that I don't think is going to be like titleable and thumbnailable. And then there's like the main stuff that goes up on the YouTube. If you want to keep up with the Happy Hour segment, which is just kind of like, more vibey, you got to catch it live at 12:30 to 2. Or if you want VOD access to those things, it's they're archived on Patreon, YouTube members, and Twitch. If you pay in the appropriate spots, please consider supporting because this this stream will end someday, right? Because this is way less lucrative than just like working a job. And the day that this stream ends is kind of marked in my head by like a dollar value in my bank account, right? So every dollar that I make doing this extends the life of the stream by some amount, some unknown, kind of hard to quantify amount, but it does. So consider supporting if you want to keep this around. But if you don't, no worries. I'll just go back to work one day sooner. It doesn't really matter to me. So, yeah, thanks. Let's say YouTube, peace out, and Twitch, let's find someone to raid.